All right, so this is CS50, and this is week 1, the one in which you learn a new language, which is something we technically said last week, at least if you've never played with this graphical language known as Scratch before, which itself was a programming language. But today, as promised, we transition to something a little more traditional, a little more text-based, not puzzle piece or block-based, known as C. This is an older language. It's been around for decades, but it's a language that underlies so many of today's more modern languages, among them something called Python that we'll also come to in a few weeks' time. Indeed, at the end of the semester, the goal is for you to feel that you've not learned Scratch, you've not learned C, or even Python for that matter, but fundamentally that you've learned how to program. Unfortunately, when you learn how to program with a more traditional language like this, there's just so much distraction. Last week, I described all of the syntax, all of the weird punctuation that you see in this, like the hash symbol, these angle brackets, parentheses, curly braces, backslash n, and more. Well, today, we're not going to reveal what all of those little particulars mean, but by next week, will this no longer look like the proverbial Greek to you, a language that presumably you've never actually seen or typed before. But to do that, we'll explore some of the very same topics as last week. So recall that via Scratch, and presumably via problem set 1, we took a look at things called functions that are actions or verbs, and related to functions were arguments like inputs, and related to some functions were return values like outputs. Then we talked a bit about conditionals, forks in the road, so to speak, Boolean expressions, which are just yes-no questions or true-false questions, loops, which let you do things again and again, variables, like in math, that let you store values temporarily, and then even other topics still. So if you were comfortable on the heels of problem set 0 and last week, realize that all of these topics are going to remain with us. So really today is just about acquiring all the more of a mental model for how you translate those ideas into presumably a very cryptic new syntax. A new syntax, frankly, that's actually more simple in some ways than your own human language, be it English or something else, because there's far fewer vocabulary words. There's actually far less syntax that you might have in, say, a typical human language. But you need to be, with these computer languages, all the more precise so that you're most ultimately correct. And ultimately, we'll see, too, your code is successful along a few other lines as well. So if you think about like the last time you kind of wandered around not really knowing what you were doing or encountered something new, might not have been that long ago, entering Harvard Yard for the very first time, or Old Campus or the like, be it in Cambridge or New Haven. You didn't really need to know how to do everything as a first year. You didn't need to know who everyone was, where everything was, how Harvard or Yale or anything else for that matter worked. You sort of got by day to day by just focusing on those things that matter. And anything you didn't really understand, you sort of turn a blind eye to until it's important. And that's indeed what we're going to do today. And really for the next several weeks, we'll focus on details that are initially important and try to wave our hands, so to speak, at details that, yeah, eventually we'll get to, might be interesting, but for now they might be distractions. And by distractions, I really mean some of that syntax to which I alluded earlier. So by the end of today, and really by the end of problem set 1, your first foray presumably into this language called C, you'll have written some code. And you'll be asking yourself, we'll be asking yourselves, just how good is that code? Well, first and foremost, per last week, be it in Scratch or phone book form, like code ultimately needs to be correct, to be well done, right? You want the problem to be solved correctly, so that one sort of goes without saying. And along the way, this term will provide you with tools and techniques, so you don't have to just sit there sort of endlessly trying an input, checking the output, trying another input, checking the output. There's a lot of automation tools in the real world, and in this class and others like it, that'll help facilitate you answering that question for yourself. Is my code correct, according to our specifications or the like? But then something that's going to take more time, and you're probably not going to feel 100% comfortable with the first week, the first weeks, is just how well designed your code is. It's one thing to sort of speak English or write English, but it's another thing, or any language for that matter, but it's another thing to speak it or write it well. And we spent all these years in middle school, high school, presumably, writing papers and other documents, getting grades and feedback on them as to how well formulated your arguments were, how well structured your paper was, and the like. And there's that same idea in programming. It doesn't matter necessarily that you've just solved a problem correctly. If your code is a complete visual mess, or if it's crazy long, it's going to be really hard for someone else to wrap their mind around what your code is doing, and indeed to be confident if it is correct. And honestly, you, the next morning, the next year, the next time you look at that code, might have no idea what you yourself were even thinking. But you will if you focus, too, on designing good code, getting your algorithms efficient, getting your code nice and clean, and even making sure your code looks pretty, which would describe as a matter of style. So in the sort of written human world, having punctuation in the right place, capitalization and the like, the sort of way you write an essay, but not necessarily send a text message, relates to style, for instance. And so good style in code is going to have a few of these characteristics that are pretty easily taught and remembered, but you just have to start to get in the habit of writing code in a certain way. So these three axes, so to speak, correctness, design, and style, are really the overarching goals when writing code that ultimately is going to look like this. So this program we conjectured last week does what if you run it on a Mac or PC or somewhere else, presumably? What does it do? Yeah. It just prints hello world. And honestly, that's kind of atrocious that you need to hit your keyboard keys this many times with this cryptic syntax just to get a program to say hello world. So a spoiler, in a few weeks' time when we introduce other more modern languages like Python, you can distill this same logic into literally one line of code. And so we're getting there ultimately, but it's helpful to understand what it is that's going on here, because even though this is a pretty cryptic syntax, there's nothing after this week and really next week that you shouldn't be able to understand, even about something that right now looks a little something like this. So how do you write code? Well, I've given us sort of the answer to a problem. How do you print hello world on the screen? So what do I do with this code? Well, we're in the habit of typically writing things with like Microsoft Word or Google Documents. And yeah, I could open up Word or Google Docs or Pages or the like and just literally transcribe that character for character, save it, and boom, I've got a program. But the problem, per last week, is that computers only understand or speak what other language, so to speak? Yeah, so binary, zeros and ones. And so this obviously is not zeros and ones. So it doesn't matter if I put it in a Word doc, Google Doc, Pages file, or the like. The computer's not going to understand it until I somehow translate it to zeros and ones. And honestly, none of those tools that I rattled off are really appropriate for programming. Why? Well, they come with features like boldfacing and italics and sort of fluffy aesthetic stuff that has no functional impact on what you're trying to do with your code. And they don't have the ability, it would seem, to convert that code ultimately to zeros and ones. But tools that do have this capability might be called integrated development environments, or IDEs, or more simply, text editors. A text editor is a tool that a programmer uses perhaps every day to write their code. And it's a simple program. Here, for instance, a very popular one called Visual Studio Code, or VS Code. And at the top here, you see that I've actually created in advance, before class, a very simple empty file called hello.c. Why? Well, .c indicates by convention that this is going to be a file in which there is C code. It's not .docx, which would mean in this file is a Microsoft Word document, or .pages is a pages file. This is .c, which means in this file is going to be text in the language called C. This number 1 here is just sort of an automatic line number that's going to help me keep track of how long or short this program is. And the cursor is just blinking there, waiting for me to start typing some code. Well, let me go ahead and type out exactly the same code. For me, it comes pretty comfortably from memory, so I'm going to go ahead and include something called standard io.h. More on that later. I'm going to sort of magically type int main void, whatever that means. We'll come back to that later. One of these curly braces, and then a sibling there that closes the same. Then I'm going to hit tab to indent a few spaces, and then I'm going to type not print, but printf. Then hello, comma, world, \n, close quote, close parenthesis, semicolon. And I dare say this was essentially the very first program I wrote some 25 years ago. I wrote it to say, hi, CS50. Now it just says the more canonical, conventional hello world. But that's it. That's my very first program. And all I need to now do is maybe hit Command-S or Control-S to save the file. And voila, I am a programmer. The catch, though, is, like, OK, how do I run this? Like on your Mac or PC, how do you run a program? Well, usually double-click an icon. On your phone, you tap an icon. In this environment that we're using and that many programmers, dare say most programmers use, you don't have immediately a nice, pretty icon to double-click on. That's very user-friendly, but it's not very necessary, especially when you get more comfortable with programming. You're going to want to type commands because it's just faster than pointing and clicking a mouse. And you're going to want to automate things, which is a lot easier if it's all command or text-based as opposed to mouse and muscular movements. And so here, I have my program. It lives in this file called hello.c. I need to now convert it, though, to zeros and ones. Well, how do I go about doing this, and how am I going to get from those this so-called code, or source code, as it's conventionally called, to this, these zeros and ones that we'll now start calling machine code? The zeros and ones from last week can be used not only to represent numbers and letters, colors, audio, video, and more. It can also represent instructions to a computer, like print, or play a sound, or delete a file, or save a file. All the sort of basics of a computer somehow can be represented by other patterns of zeros and ones. And just like last week, it depends on the context in which these numbers are stored. Sometimes they're interpreted as numbers, like in a spreadsheet. Sometimes they're interpreted as colors. Sometimes they're interpreted as instructions, commands to your computer to do very low-level operations like print something on the screen. So fortunately, like last week's definition of like computer science of problem solving is a nice mental model for exactly the goal at hand. I have some input, aka source code. I want to output ultimately machine code, those zeros and ones. I certainly don't want to do this kind of process by hand. So hopefully there's an algorithm implemented by some special program that does exactly that. And those of you who do have some prior experience, this program might be called a compiler. So a few of you have indeed programmed before. Not all languages use compilers. C, in fact, is a language that does use a compiler. And so I just need to find myself on my computer somewhere, presumably, a so-called compiler, a program whose purpose in life is to convert one language to another. And source code, written textually in C, like we saw a moment ago, is source code. The machine code is the corresponding zeros and ones. So let me go back to the same programming environment called Visual Studio Code, or VS Code. This is typically a program you or any programmer on the internet can download onto their own Mac or PC and be on their way with whatever computer you own writing some code. A downside, though, of that approach is that all of us have slightly different versions of Macs or PCs. We have slightly different versions of operating systems. They may or may not be up to date. It's just sort of a technical support nightmare to create a uniform environment, especially for like an introductory class where everyone should ideally be on the same page so we can get you up and running quickly. And so I'm actually using a cloud-based version of VS Code, something that you only need a browser to access, and then you could be on any computer today or tomorrow. By the end of the semester, we're going to get you out of the cloud, so to speak, as best we can, and get you onto your own Mac or PC so that after this class, especially if it's the only CS class you ever take, you feel like you can continue programming in any number of languages, even with CS50 behind you. But for now, wonderfully, the browser version of VS Code should pretty much be identical to what the eventual downloadable version of the same would be. And you'll see in problem set 1 how to access this and how to get going yourself with your first programs. But I haven't mentioned this bottom part of the screen, And this is an area where we have what's called a terminal window. So this is sort of old school technology that allows you with a keyboard to interact with a computer, wherever it may be, on your lap, in your pocket, or even, in this case, in the cloud. So on the top-hand portion of this screen is my code, my text editor, like tabbed windows, like in many programs where I can just create files and write code. The bottom of the screen here, my so-called terminal window, gives me the ability to run commands on a server that currently I have exclusive access to. So because I log into VS Code with my account online, I have my own sort of virtual server, if you will, in the cloud, otherwise known as, in this context, a container. This has its own operating system for me, its own hard drive, if you will, where I can save and create files of my own separate from yours and vice versa. And it's at this very simple prompt, which is conventionally, but not always, abbreviated by a $, has nothing to do with currency. It just means type your commands here. This is where I'm going to be able to type commands like compile my source code into machine code. So it's a command line interface, or CLI, on top of an operating system that you might not have ever used or seen, but it's very popular, called Linux. Odds are almost all of us in this room are using Mac OS or Windows right now, but we're all going to start using an operating system called Linux, which is in a family of operating systems that offer not only this command line interface, but are used not just for programming, but for serving websites and developing applications and the like. And it's indeed a familiar and very powerful interface, as we'll see. So how do I go about making this file, hello.c, into a program? There's no icon to double click, but there is a command. I can type make hello at this $ prompt, go ahead and hit enter, and nothing appears to happen. But that's a good thing. And as we'll see in programming, almost always, if you don't see anything go wrong, that means everything went right. So this is going to be a rarity at first, but this is a good thing that it just seems to do nothing. But now, there is in the folder, in my account on the cloud, a file called hello. And it's a bit of a weird command, but you'll get familiar with it before long. Dot just means go into my current folder. /hello means run the program called hello in this current folder. So /hello and then enter, and voila, now I'm actually not just programming, but running my actual code. So what have I just done? Let me go ahead and do this. I'm going to go ahead and open up the sidebar of this program, and you'll see in problem set 1 how to do this. And this might look a little different based on your own configuration. Even the color scheme I'm using might ultimately look different from yours because it supports nice colorful themes, so you can have different colors and brightnesses depending on your mood or the time of day. What I've opened here, though, is what is called in VS Code Explorer, and this is just all of the files in my cloud account. And there's not many right now. There's only 2. One is the file called hello.c, and it's highlighted because I've got it open right there. And the other is a file called hello, which is brand new and was created when I ran that command. And what's now worth noting is that now things are getting a little more like macOS and Windows. Like on the left-hand side, you have a GUI, a graphical user interface. But on the bottom here, again, you have a CLI, command line interface. These are just different ways to interact with computers. And you'll get comfortable with both. And honestly, you're certainly familiar and comfortable with GUIs already. So it's a command line one with which we'll spend some time. Now, suppose that I just wanted to do something more than compile this program. Suppose I wanted to go ahead and remove it. Like, no, I made a mistake. I want to say hello CS50, not hello world. I could just hover up here like in any software, and I could right-click, and I could poke around, and there, delete permanently. So most of us might have that instinct on a Mac or PC. You right-click or control-click, and you poke around. But in a command line interface, let me do this instead. The command for removing or deleting a file in the world of Linux, this other operating system, is just to type rm for remove, and then hello, enter. It's a somewhat cryptic confirmation message, but this just means, are you sure? I'm going to go ahead and type Y for yes, and now when I hit enter, watch what happens at top left in the Explorer, the GUI, the graphical interface. Voila, it disappears. Right, not terribly exciting, but this just means this is a graphical version of what we're seeing here. And in fact, if you want to never use the GUI again, I'll go ahead and close it with a keyboard shortcut here. You can forever just type ls for list and hit enter, and you will see in the command line interface all of the files in your current folder. So anything you can do with a mouse, you can do with this command line interface, and indeed we'll see many more things that you can do as well. But the inventors of this and this operating system and its predecessors were very succinct. Like the command is rm for remove, the command is ls for list. It's very terse. Why? Because it's just faster to type. So before we forge ahead with making something more interesting than just hello world, let me pause here to see if there's questions on source code or machine code or compiler or this command line interface. Yeah. Really good question. And let me recap. If I were to make changes to the program, run it, and then maybe make other changes and try to rerun it, would those changes be reflected, even though it reworded slightly? Well, let's do this. I already removed the old version, so let me go ahead and point out that if I do /hello now, I'm going to see some kind of error because I just deleted the file. No such file or directory, so it's not terribly user-friendly, but it's saying what the problem is. Let me go ahead and remake it by typing make hello. Now, if I type ls, I'll see not one but 2 files again, and one of them is even green with a little asterisk to indicate that it's executable. It's sort of the textual version of something you could double-click in our human world. So now, of course, if I run hello, we're back where I started, hello world. But now suppose I change it to hello, CS50, like I did years ago. Let me go ahead and save the file with Command-S or Control-S. Down here now, let me run /hello again, and voila. So let me ask someone else to answer that question. What's the missing step? Why did it not say hello CS50? Yeah, so I didn't compile it again. So sort of newbie mistake. You're going to make this mistake and many others before long, but now let me go ahead and remake hello, enter. It's going to seemingly make the same program, but this time when I run it, it's hello CS50. All right, any other questions on some of these building blocks? And we'll come back to all the crazy syntax I typed before long. But for now, we're focusing on just the output. Yeah. When I keep running make, it creates a new version of the machine code. So it keeps changing the hello program in the hello file, and that's it. There's no make file per se. Good question. No. If I open up that directory, you'll see that there's just the one. And it doesn't matter how many times I run make hello, 3, 4, 5, it just keeps overwriting the original. So it's kind of like just saving in the world of Google Docs or Microsoft Word or the like, but there's an additional step today. We have to then convert my words to the computers, the zeros and ones. Yeah, in front. What happens if I run hello.c? So let me go ahead and do /hello.c, which is a mistake you'll invariably make early on, permission denied. So what does that mean? This is where the error messages mean something to the people who design the operating system, but it's a little cryptic. It's not that you don't have access to the file. It means that it's not executable. This is not something you have permission to run, but you do have permission to read or write it. That is change it. Really good question. So if I have named my file hello.c, or more generally something.c, one of the things that make does is it automatically picks the file name for me. And we'll discuss this a bit more next week. Make itself is kind of the first of white lies today. Itself is not a compiler. It's a program that knows how to find and use a compiler on the system and automatically create the program. If I use, as we'll discuss next week, the actual compiler myself, I have to type a much longer sequence of commands to specify explicitly what I want the name of my program to be. Make is a nice program, especially in week 1, because it just automates all of that for us. And so here, we have now a program that very simply prints something on the screen. So let's now put this into the context of where we left off last time, in the context of Scratch and inputs and outputs. So we discussed last time, of course, functions and arguments. Functions, again, are those actions and verbs like say or ask or the like. And the arguments were the inputs to those functions, generally in those little white ovals that in Scratch you could type words or numbers into. We'll see in all of the languages we're going to see this term have that same capability, and let's just start to translate one of these things to another. So for instance, let's put this same program in C in the context of Scratch. This is what hello world looked like last week in the form of one function. This week, of course, it looks like print, and then the parentheses, notice, are kind of deliberately designed in the world of Scratch to resemble that same shape. Even though this is a white oval, you kind of get that it's kind of evoking that same idea with the parentheses. Technically, the function in C, it's not called say, it's not even called print, it's called printf. The F stands for formatted, but we'll see what that means in a moment. But printf is the closest analogous function for say in the world of C. Notice if though you want to print something like hello world or hello CS50 in C, you don't just write the words as we did last week. You also had to add what, if you notice already what's missing from this version? Yeah, so the double quotes on the left and the right. So that's necessary in C. Whenever you have a string of words, and I'm using that word deliberately, whenever you have multiple words like this is known as a string, as we'll see, and you have to put it in double quotes. Not single quotes, you have to put it in double quotes. There's one other stupid thing that we need to have in my C code in order to get this function to do something ultimately, which is what? Semicolon. So just like in our human world, you eventually got into the habit of using, at least in formal writing periods, semicolon is generally what you use to finish your thought in the world of programming with C. All right, so we have that function in place. Now, what does this really fit into in terms of the mental model? Well, functions take arguments, and it turns out functions can have different types of outputs. And we've actually seen both already last week. One type of output from a function can be something called a side effect, and it generally refers to something visual, like something appearing on the screen or a sound playing from your computer. It's sort of a side effect of the function doing its thing. And indeed, last week we saw this in the context of passing in something like hello world as input to the say function, and we saw on the screen hello world. But it was kind of a one-off. It's one and done. You can't actually do anything with that visual output other than consume it visually with your human eyes. But sometimes, recall last week, we had functions like the ask block that actually returned me some value. Remember the ask, what's your name? It handed me back whatever answer the human typed in. It didn't just arbitrarily display it on the screen. The cat didn't necessarily say it on the screen. It was stored instead in that special variable that was called answer, because some functions have not side effects but return values. They hand you back an output that you can use and reuse, unlike the side effect, which again displays and that's it. You can't sort of catch it and hold on to it. So in the context of last week, we had the ask block, and that had this special answer return value. In C, we're going to see in just a moment, we could translate this as follows. The closest match I can propose for the ask block is a function that we're going to start calling getString. String is, again, a word, a set of words, like a phrase or a sentence in programming. It, too, is a function insofar as it takes input. And pretty much, this isn't always true, but very often when you have a word in C followed by an open parenthesis and a closed parenthesis, it's most likely the name of a function. And we're going to see that there's some exceptions to that, but for now, this indeed looks like a function because it matches that pattern. If I want to ask the question, what's your name, question mark, and I'm even going to deliberately put a space there just to kind of move the cursor a little bit over so that the human isn't typing literally after the question mark, so that's just a nitpicky aesthetic, this is perhaps the closest analog to just asking that question. But because the ask block returns a value, the analog here for getString is that it too returns a value. It doesn't just print the human's input, it hands it back to you in the form of a variable, aka a return value, that I can then use and reuse. Now, ideally, it would be as simple as this, literally saying answer on the left equals, and this is where things start to diverge from math and sort of our human world. This equal sign, henceforth, is not the equal sign. It is the assignment operator. To assign a value means to store a value in some variable. And you read these things weirdly right to left. So here is a function called getString. I claim that it's going to return to you whatever the human types in as their name. It's going to get stored over here on the left because of this so-called assignment operator. That yes is an equal sign, but it doesn't mean equality in this context. It makes things equal, but it does so by copying the value on the right into the thing on the left. Unfortunately, we're not quite done yet with C, and this is where, again, it gets a little annoying at first, where Scratch just let us express our ideas without so much syntax. In C, when you have a variable, you don't just give it a name like you did in Scratch. You also have to tell the computer in advance what type of value it is storing. String is one such type of value. Int for integer is going to be another. And there's even more than that we'll see today and beyond. And this is partly an answer to the question that came up one or more times last week, which was, how does a computer distinguish this pattern of zeros and ones from this? Like, is this a letter, a number, a color, a piece of video? And I just claimed last week that it totally depends on the program. It depends on the context. And that's true. But within those programs, it often depends on what the human programmer said the type of the value is. If this specifies it's a string, which means interpret the following zeros and ones that are stored in my program as words or letters more generally. If it said int for integer, it would be implying by the programmer treat the following zeros and ones in my program as a number, an integer, not a string. So here's where this week, unlike with Scratch, which just kind of figures out what you mean, with C in a lot of languages, you have to be this pedantic and tell it what you mean. There's still one stupid thing missing from my code here. What's still missing here? Yeah? And we still need the stupid semicolon. And I'm sort of impugning it here because honestly, these are the kinds of stupid mistakes you're going to make today, tomorrow, this weekend, next week, a few weeks from now, until you start to notice this and recognize it as well as you do English or whatever your spoken language is. Yeah, question. Good question. Suppose I mix apples and oranges, so to speak, and I try to put a string in an int or an int in a string. The compiler is going to complain. So when I run that make command as I did earlier, it's not going to be nice and blissfully quiet and just give me another prompt. It's going to yell at me with honestly a very cryptic-looking error message until we get the muscle memory for reading it. Other questions? What happens to the \n? So we'll come back to that in just a moment if we may, because I have deliberately omitted it here, but we did have it earlier, and we'll see the different behavior in a sec. Other questions? Yeah, not at all nitpicky. These are the kinds of things that just matter, and it's going to take time to recognize and develop this muscle memory. Everything I've typed here, except for the W at the moment, is lowercase. And the W is capitalized just because it's English. Everything else is lowercase. And this kind of varies by language and also context. So in many languages, the convention is to use all lowercase letters for your variable names. Other languages might use some capitals as well, but we'll talk about that before long. But this is the kind of thing that matters, and it's hard to see at first, especially when a little s doesn't look that different, when it's on your tiny laptop screen from a capital S, but you'll start to develop these instincts. All right, so besides this particular block, let's go ahead and consider how we can go about implementing this now in code. So let me switch back to VS Code here. This was the program I had earlier, and let me go ahead and undo my CS50 change, and this time just rerun make on hello with the original version with the \n. Enter. Nothing bad seems to have happened, so /hello. Enter. Hello world. Now, if you're curious, this is a good instinct to start to acquire. What happens if I get rid of this? Well, I'm probably not going to break things too badly, so let's try. Let me go ahead now and do make hello. Still compile, so it's not a really bad mistake. So let me go ahead and run /hello. What's the difference here? Yeah, what do you see that's different? Yeah, the $sign, my so-called prompt, stayed on the same line. Why? Well, we can presumably infer now that the \n is some fancy notation for saying create a new line, move the cursor, so to speak, to the next line. Notice that the cursor will move to the next line in my terminal window. If I keep hitting it, it just automatically, by nature of hitting enter, does it. But it'd be kind of stupid if when you run a program in this world, simple as it is, if like the next command is now weirdly spaced in the middle of the terminal with a $sign, it just looks sloppy, right? It's really just an aesthetic argument. And notice that it's not acceptable or correct to do this, to hit enter there. Let me go ahead and save that, though, and see what happens. Let me go ahead now and run make hello, enter. Oh my god, like 4 errors. This is like, what, 10 lines of errors for like a 1-line program? And this is where, again, you'll start to develop the instinct for just reading this stuff. These kinds of tools, like the compiler tool we're using, were not designed necessarily with user-friendliness in mind. That's changed over the decades, but certainly early on, it's really just meant to be correct and precise with its errors. So what did I do here? Missing terminating close quote character. Long story short, when you have a string in C, your double quotes just have to be on the same line, just because. Now, there's the slight white lie. There's ways around this, but the best way around it is to use this so-called escape sequence. To escape something means generally to put a / and then a special symbol like n for new line. And this is just the agreed-upon way that humans decades ago decided, OK, you don't just hit your enter key. You instead put \n, and that tells the computer to move the cursor to the new line. So again, kind of cryptic, but once you know it, like that's it. It's just another word in our vocabulary. So now let me transition to making my program a little more interactive. Instead of just saying hello world, let me change it like last week to say hello David, or whoever's interacting with the program. So I'm going to do string answer get string, quote unquote, what's your name? I'm not going to bother with a new line here. I could. This is now just a judgment call. I deliberately want the human to type their name on the same line, just because. And how do I now print this? Well, last week, recall, we used say, and then we used the other block called join. So the idea here is the same, but the syntax this week is going to be a little different. It's going to be printf, which prints something on the screen. I'm going to go ahead and say hello, comma, and let me just go with this initially, with the \n, semicolon. Let me go ahead and recompile my code. Whoops. Damn, it doesn't work still. Look at all these errors. Like, there's more errors than code I wrote. But what's going on here? Well, this is actually a mistake you'll see somewhat often, at least initially. And let's start to glean what's going on here. So here, if I look at the very first line of output after the $sign, so even though it jumped down the screen pretty fast, I wrote make hello at the $sign, prompt, and then here's the first error. On hello.c, line 5, technically character 5, but generally line is enough to get you going. There's an error, use of undeclared identifier string. Did you mean standard in? So I didn't. And this is not an obvious solution at first, but you'll start to recognize these patterns in error messages. It turns out that if I want to use string, I actually have to do this. I have to include another library up here, another line of code rather, called CS50's. We'll come back to what this means in just a moment. But if I now retroactively say, all right, what does standard IO do for us up here? Before I added that new line, What is standard I/O doing? Well, if you think back to Scratch, there were a few examples with like the camera and with the speech to the text to voice. Remember, I had to poke around in like the extensions button, and then I had to load it into Scratch. It didn't come natively with Scratch. C is quite like that. Some functions come with the language, but for the most part, if you want to use a function, an action or a verb like printf, you have to load that extension, so to speak, that more traditionally is called a library. So there is a standard I/O library, stdio, standard I/O, where I/O just means input and output, which means just like in MIT's world, there was an extension for doing text to voice or for using your camera. In C, there's an extension, aka a library, for doing standard input and output. And so if you want to use any functions related to standard input and output, like keyboard, text from a keyboard, you have to include standard IO.h, and you have to, then can you use printf. Same goes here. GetString, it turns out, is a function that CS50 wrote some time ago, and as we'll see over the coming weeks, it just makes it way easier to get input from a user. C is very good with printf at printing output on the screen. C makes it really annoying and hard, as we'll see in a few weeks, to just get input from the user. So we wrote a function called getString, but the only way you can use that is to load the extension, aka load the library called CS50. And we'll come back in time, like why is it .h, why is it a hash symbol, but for now, standard IO is a library that gives you access to printf and input and output related stuff. CS50 is a second library that provides you with access to functions that don't come with C, that include something like getString. So with that said, we've now kind of teased apart at a high level what lines 2 and now 1 are doing. Let me go ahead and rerun make hello. Now it worked. So all those crazy error messages were resolved by just one fix. So key takeaway is not to get overwhelmed by the sheer number of errors. Let me now do /hello. And if I type in my name, what am I going to see? What do you think? Yeah, hello, answer, because the computer is going to take me literally. And it turns out that if you just write hello, answer all in the double quotes, you're really just passing English as the input to the printf function. You're not actually passing in the variable. And unfortunately in C, it's not quite as easy to plug things in to other things that you've typed. Remember in Scratch, there was not just a say block, but the join block, which was kind of pretty. It does, you can combine apples and oranges, or both apple and banana. Then we changed it to hello, and then the answer that the human typed in. In C, the syntax is going to be a little different. You tell the computer inside of your double quotes that you want to have a placeholder there, so-called format code. %s means, hey, computer, put a string here eventually. Then, outside of your quotes, you just add a comma, and then you type in whatever variable you want the computer to plug in at that %s location for you. So %s is a format code, which serves as a placeholder. And now the printf function was designed by humans years ago to figure out how to do the apple and banana thing of joining. And now the printf function was designed by humans years ago to figure out how to do the apple and banana thing of joining to for you. So %s is a format code, which serves as a placeholder. And now the printf function was designed by humans years ago to figure out how to do the apple and banana thing of joining two words together. It's not nearly as user-friendly as it is in Scratch, but it's a very common paradigm. So let me try and rerun this now. Make hello. No errors, that's good. /hello, what's my name, David? If I type enter now it's hello, David. And the printf, here's the f in printf, it formats its input for you by using these placeholders for things like strings, represented again by %s. So a quick question then. If I focus here on line 7 for just a moment and even zoom in here, how many inputs is printf taking as a function? A moment ago, I'll admit that it was taking one input, hello world, quote unquote. How many inputs might you infer printf is taking now? 2. And it's implied by this comma here, which is separating the first one, quote unquote hello, %s, from the second one, answer. And then just as a quick safety check here, why is it not 3? Because there's obviously 2 commas here. Why is it not actually 3 arguments or inputs? Exactly. The comma to the left is actually part of my English grammar. That's all. So same syntax. And again, here's where programming can just be confusing early on because we're using the same special punctuation to mean different things. It just depends on the context. And so now's actually a good time to point out all of the somewhat pretty colors that have been popping up on the screen here. Even though I wasn't going to like a format menu, I wasn't bold-facing things, I certainly wasn't changing things to red or blue or whatnot. That's because a text editor, like VS Code, syntax highlights for you. This is a feature of so many different programming environments nowadays. VS Code does it as well. If your text editor understands the language that you're programming in, C in this case, it highlights in different colors the different types of ideas in your code. So for instance, string and answer here are in black, but getString, a function, is in this sort of nasty brown yellow here right now, but that's just how it displays on the screen. The string though here in red is kind of jumping out at me, and that's marginally useful. The %s is in blue. That's kind of nice because it's jumping out at me. And so it's just using different colors to make different things on the screen pop so you can focus on how these ideas interrelate and honestly, when you might make a mistake. For instance, let me accidentally leave off this quote here, and now all of a sudden, everything, notice, if I delete the quote, the colors start to get a little awry, but if I go back there and put it back, now everything's back in place. What's another feature of this text editor? Notice when my cursor is next to this parenthesis, which demarcates the end of the inputs to the function, notice that highlighted in green here is the opening parenthesis. Why? It's just a visually useful thing, especially when you start writing more and more code, just to make sure your parentheses are lining up. And that's true for these curly braces over here on the left and the right. We'll come back to those in a moment. If I put my cursor there, you can see that these things correspond to one another. So it's nothing in your code fundamentally, it's just the editor trying to help you, the human, program. And you can even see it, though it's a little subtle. See these 4 dots here and these 4 dots here? That's my indentation. I've configured VS Code to indent by 4 spaces, which is a very common convention. Anytime I hit the tab key, this too can help you make sure, once we have more interesting and longer programs, that everything lines up nice and neatly. All right, any questions then on printf or more? Yeah. Short answer, yes. Printf can handle more than one type of variable or value. %s is one. We're going to see %i is another for plugging in an integer. You can have multiple i's, multiple s's, and even other symbols too. We'll come back to that in just a little bit. Printf can take many more arguments than just these two. This is just meant to be representative. Yeah, over here. Can you declare variables within the printf? No. The only variable I'm using right now is answer, and it's got to be done outside the context of printf in this case. Good question. We'll see more of that before long. Yeah, in back. How do we download the CS50 library? So we will show you in problem set 1 exactly how to do that. It's automatically done for you in our version of VS Code in the cloud. If ultimately you program on your own Mac or PC, either initially or later on, it's also installable online. But if you want to ask that online or afterward, we can point you in the right direction. But pset 1 will itself. Yeah. String is the type of the variable, or more properly, the data type of the variable. Int is another keyword I alluded to earlier. I haven't used it yet. Int for integer is going to be another type or data type of variable. Yeah. Good question. Could I go ahead and just plug in this function, kind of like we did in Scratch, getting rid of the variable altogether, and just do this, which recall is reminiscent of what I did in Scratch by plopping block on top of block on block? Am I answering that right? Can I put string in front of getString? No. You only put the word string in front of a variable that you want to make string. And even though I'm apparently answering the wrong question, let me go ahead and zoom out, save this, do make hello again. Seems to compile OK. If I run /hello, type in David, voila, that too works. And so actually, let's go down this rabbit hole for just a moment. Clearly, it's still correct, at least based on my limited testing. Is this better designed or worse designed? Let's open that question like we did last week, yeah? Yeah, I kind of agree with that. Reasonable people could disagree, but I do agree that this seems harder to read because, like, I start reading here, but wait a minute, getString is going to get used first, and then it's going to give me back a value. So yeah, it just feels like it was nicer to read top to bottom, I would say. Your thoughts? Yeah, and so this is useful if I only want to print out the person's name once. If I want to use it later in a longer program, I'm out of luck, and so I haven't saved it in a variable. So I think, long story short, we could sort of debate this all day long, but in this case, like, if you can make a reasonable argument one way or the other, like, that's a pretty solid ground to stand on. But invariably, reasonable people are going to disagree, whether first-time programmers or many years after that. So let's frame this one last example in the context of the same process of taking inputs and outputs. The functions we've been talking about all take inputs, otherwise now known as arguments or parameters, pretty much synonymous. That's just a fancy word for an input to a function. And some functions have either side effects, like we saw, printing something, saying something on the screen sort of visually or audibly, or they return a value, which is a reusable value, like name or answer in this case. If we look then at what we did last time, in the world of Scratch last week, the input was what's your name, the function was ask, and the return value was answer. And now let's take a look at this block, which is honestly a more user-friendly version of what we just did with the %s. Last week we said say, then join, then hello and answer. But the interesting takeaway there was not how to say hello anything. It was the fact that in Scratch 2, the output of one function, like the green join, could become the input to another function, the purple say. The syntax in C is admittedly pretty different, but the idea is essentially the same. Here, though, we have hello, a placeholder, but we have to, in this world of C, tell printf what we want to plug in for that placeholder. It's just different, but that's the way to do it. When we get to Python and other languages later in the term, there's actually easier ways to do this, but this is a very common paradigm, particularly when you want to format your data in some way. All right, let's then take a step back to where we began, which was with that whole program, which had the include, and it had int, main, void, and all of this other cryptic syntax. This Scratch piece last week was kind of like the go-to whenever you want to have a main part of your program. It's not the only way to start a Scratch program. You could listen for clicks or other things, not just a green flag, but this was probably the most popular place to start a program in Scratch. In C, the closest analog is to literally write this out. So just like last week, if you were in the habit of dragging and dropping when green flag clicked, as a C programmer, the first thing you would do is after creating an empty file, like I did with hello.c, you'd probably type int main void, open curly brace, close curly brace, and then you can put all of your code inside of those curly braces. So just like Scratch had this sort of magnetic nature to it, where the puzzle pieces would snap together, C, as a text-based language, tends to use these curly braces, one of them opened, the other one closed, and anything inside of those braces, so to speak, is part of this puzzle piece, aka main. So what was atop them? We went down this rabbit hole a moment ago with these things called header files, even though I didn't call them by this name. But indeed, when we have a whole program in Scratch, super easy. Just have the when green flag clicked and then say hello world. There's no special syntax. After all, it's meant to be very user-friendly and graphical. In C, though, you technically can't just put int main void printf hello world. You also need this because, again, you need to tell the compiler to load the library, code that someone else wrote, so that the compiler knows what printf even is. You have to load the CS50 library whenever you want to use getString or other functions like getInt, as we'll soon see. Otherwise, the compiler won't know what getString is. You just have to do it this way. The specific file name I'm mentioning here, standardIO.h, CS50.h, is what C programmers call a header file. We'll see eventually what's inside of those files, but long story short, it's like a menu of all of the available functions. So in CS50.h, there's a menu mentioning getString, getInt, and a bunch of other stuff. And in standardIO.h, there's a menu of functions among which are printf. And that menu is what prepares the compiler to know how to implement those same functions. All right, let me pause here. Question? Not quite. A library provides all of the functionality we're talking about. A header file is the very specific mechanism via which you include it. And we'll discuss this more next week. For now, they're essentially the same, but we'll discuss nuances between the two next week. Yeah, the library would be standard.io. The library would be CS50. The corresponding header file is standard.io.h, CS50.h. Indeed. Other questions? Yeah. Indeed, that too is on the menu. We'll come back to that. But the word string, incredibly common in the world of programming. It's not a CS50 idea, but in C, there's technically no such data type as string by default. We have sort of conjured it up to simplify the first few weeks. That's a training wheel that we'll very deliberately in a few weeks take away, and we'll see why we've even been using getString and string, because C otherwise makes things quite more challenging early on, which then gets besides the point for us. Yeah. Yes, early on, you will have to use whatever's prescribed by the specification. That will include CS50's functions. Long story short, you referred, I think, a moment ago to another function called scanf. We won't talk about for a few weeks. Long story short, in C, it's pretty easy and possible to get input from a user. The catch is that it's really easy to do it dangerously. And C, because it's an older, lower-level language, so to speak, that gives you pretty much ultimate control over your computer's hardware, it's very easy to make mistakes. And indeed, that's, too, why we use the library, so your code won't crash unintendedly. All right, so with this in mind, we have this now mapping between the Scratch version and the other. Let me just give you a quick tour of some of the other placeholders and data types that we'll soon start seeing as we assemble more interesting programs. In the world of Linux, here's a non-exhaustive list of commands with which you'll get familiar over the next few weeks by playing with problem sets. We've only seen 2 of these so far, ls for list, rm for others, but I mention them now just so that it doesn't feel too foreign when you see them on screen or online in a problem set. CP is going to stand for copy. Makedir is going to stand for make directory. MV is going to stand for move or rename. rmdir is going to be remove directory. And CD is going to be for change directory. And let me show you this last one here first, only because it's something you'll use so commonly. If I go back to my code here on the screen, I'm going to go ahead and reopen the little GUI on the left-hand side, the so-called Explorer, revealing that I've got 2 files, hello and hello.c. So nothing has changed since there. Suppose now that it's a few weeks into class and I want to start organizing the code I'm writing so that I have a folder for this week or next week, or maybe a folder for problem set 1, problem set 2. I can do this in a few ways. In the GUI, I can go up here and do what most of you would do instinctively on a Mac or PC. You look for like a folder icon, you click it, and then you name a folder like pset1, enter. Voila, you've got a folder called pset1. I can confirm as much with my command line interface by typing what command? How can I list what's in my folder? Yeah, so ls for list, and now I see hello, and it's green with an asterisk because that's my executable, my runnable program, hello.c, which is my source code, and now pset1 with a slash at the end, which just implies that it's indeed a folder. All right, I didn't really want to do it that way. I'd like to do it more advanced. So let me go ahead and right-click on pset1, delete permanently. I get a scary irreversible error message, but there's nothing in it, so that's fine. Now I've deleted it using the GUI. But now let me go ahead and start doing the same thing from the command line. And if you're wondering how things keep disappearing, if you hit Control-L in your terminal window or explicitly type clear, it will delete everything you previously typed just to kind of clean things up. In practice, you don't need to be doing this often. I'm doing it just to keep our focus on my latest commands. If I do, what was the command to make a new directory? Yeah, so make directory. Let me create pset1, enter, and notice it left. There's my pset1. If I want to get a little overzealous, plan for next week, here's my pset2 directory. Suppose now I want to open those folders, one on Mac or PC or in this GUI. I could double click on it like this, and you'd see this little arrow is moving. It's not doing anything because there's nothing in there, but that's fine. But suppose, again, I want to get more comfortable with my command line. Notice if I type ls now, I see all 4 same things. Let me change directories with cd space pset1, enter. And now notice 2 things will have happened. 1, my prompt has changed slightly to remind me where I am, just to keep me sane so that I don't forget what folder I'm actually in. So here is just a visual reminder of what folder I'm currently in. If I type ls now, what should I see after hitting enter? Nothing, because I've only created empty folders so far, and indeed, I see nothing. If I wanted to create a folder called Mario for a program that might be called Mario this week, I can do that. Now if I type ls, there's Mario. Now if I do cd Mario, notice my prompt's going to change to be a little more precise. Now I'm in pset1/Mario. And notice what's happening at top left. Nothing now because these folders are collapsed. But if I click the little triangle, there I see Mario. Nothing's going on in there because there's no files yet. But suppose now I want to create a file called mario.c. I could go up here. I could click the little plus icon and use the GUI. Or I can just type code mario.c. Voila. That creates a new tab for me. I'm not going to write any code in here yet, but I am going to save the file. And now at top left, you'll see that mario.c appears. So at some point, you can eventually just close the Explorer, because again, it's not providing you with any new information. It's maybe more user-friendly, but there's nothing you can't do at the command line that you could do at the GUI. All right, but now I'm kind of stuck. How do I get out of this folder? In my Mac or PC world, I'd probably click the back button or something like that, or just close it and start all over. In the terminal window, I can do cd ... is a nickname, if you will, for the parent directory. That is the previous directory. So if I hit enter now, notice I'm going to close the Mario folder, aka directory, and now I'm back in pset1. Or if I want to be fancy, let me go back into Mario temporarily. If I type ls, there's mario.c, just to orient us. If I want to do multiple things at a time, I could do cd // which goes to my parent to my grandparent, all in one breath. And voila, now I'm back in my default folder, if you will. And one last little trick of the trade, if I'm in pset1/Mario, like I was a moment ago, and you're just tired of all the navigation, if you just type cd and hit enter, it'll whisk you away back to your default folder. And you don't have to worry about getting there manually. Recall a bit ago, though, that I was running hello as this, /hello. If ... refers to my parent, perhaps infer here syntactically, what does a single dot mean instead? It means this directory, your current directory. Why is that necessary? It just makes super explicit to the computer that I want the program called hello that's installed here, not in some random other folder on my hard drive, so to speak. I want the one that's right here instead. All right, so besides these commands, there's going to be others that we encounter over time. Those are kind of the basics. That allows you to sort of wean yourself off of a GUI, a graphical user interface, and start using more comfortably, with practice and time, a command line interface instead. Well, what about those other types? Now, back in the world of C, those commands were not C. Those are just commands specific to a command line interface, like in Linux, which, again, we're using in the cloud. It's an alternative to macOS and Windows. Back in the world of C now, we've seen strings, which are words. I mentioned int or integer, but there's others as well. In the world of C, we've seen string. We will see int. If you want a bigger integer, there's something literally called a long. If you want a single character, there's something called a char. If you want a Boolean value, true or false, there's a bool. And if you want a floating point value, a fancy way of saying a real number, something with a decimal point in it, that is what C and other languages call a float. And if you want even more numbers after the decimal point, that is more precision, you can use something called a double. That is to say, here's again an example in programming where it's up to you now to provide the computer with hints, essentially, that it will rely on to know that what is this pattern of zeros and ones? Is it a number, a letter? Is it a sound, an image, a color, or the like? These are the types of data types that provide exactly those hints. What are the functions that come in the menu that is the CS50 library? We talked about standard I/O, and that's just one function so far, printf. In the CS50 library, you can see that it follows a pattern. The CS50 library exists largely for the first few weeks of the class to make our lives easier when you just want to get user input. So if you want to get a string, like word or words from the human, you use getString. If you want to get an integer from the user, you're going to use getInt. When you want to get any of those other data types, for the most part, you use get underscore something else. And they're indeed all lowercase by convention. What about printf? If we have the ability now to store different types of data, and we have functions with which to get different types of data, how might you go about printing different types of data? Well, we've seen %s for string, %i for integer, %c for char, %f for a float or a double, those real numbers I described earlier, and then %li for a long integer. So here's the first example of like inconsistencies. In an ideal world, it would just be %l, and we'd move on. It's %li instead in this case. That's printf and some of its format codes. What more might we do? Well, in C, as we'll see, no pun intended, there's a whole bunch of operators. And indeed, computers, one of the first things they did was a lot of math and calculation. So there's a lot of operators like these. Computers, and in turn C, really good at addition, subtraction, multiplication, division, and even the % sign, which is the remainder operator. There's a special symbol in C and other languages just for getting the remainder when you divide one number by another. There are other features in the world of C, like variables, as we've seen, and there's also what is sort of playfully called syntactic sugar that makes it easier over time to write fewer characters but express your thoughts the same. So just as a single example of this, consider this use of a variable last week. Here in Scratch is how you might set a variable called counter to 0. In C, it's going to be similar. If you want the variable to be called counter, you literally write the word counter, or whatever you want it to be called. You then use the assignment operator, aka equal sign, and you assign it whatever its initial value should be here on the right. So again, the 0 is going to get copied from right to left into the variable because of that single equal sign. But this isn't sufficient in C. What else is missing on the right-hand side instinctively now, even if you've never programmed in this before? Yeah, in front. A semicolon at the end, and one other thing I think is probably missing, again, a data type. So what would you, if we can keep going back and forth here, what data type seems appropriate intuitively for a counter? Int for integer. So indeed, we need to tell the computer when creating a variable what type of data we want, and we need to finish our thought with the semicolon. So there might be a counterpart there. What about in Scratch if we wanted to increment that counter variable? We had this very user-friendly puzzle piece last time that was change counter by 1 or add 1 to counter. In C, here's where things get a little more interesting and pretty commonly done. You might do this. Counter equals counter plus 1 with a semicolon. And this is where, again, it's important to note the equal sign, it's not equality. Otherwise, this makes no sense. Counter cannot equal counter plus 1, right? Like, that just doesn't work if we're talking about integers here. That's because the equal sign is assignment. So it can certainly be the case that you calculate counter plus 1, whatever that is. Then you update the value of counter from right to left to be that new value. This, as we'll see, is a very common thing to do in programming, just to kind of count upward for whatever reason. You can write this more succinctly. This code here is what we'll call syntactic sugar, sort of a fancy way of saying the same thing with fewer words or fewer characters on the screen. This also adds 1, or whatever number you type over here, to the variable on the left. And there's one other form of syntactic sugar we're going to start seeing too, and it's even more terse than this. That too will increment counter by 1 by literally changing its value by 1, or if you change it to minus minus, subtracting 1 from it. You can't do that with 2 and 3 and 4, but you can do it by default with just plus plus or minus minus, adding or subtracting 1. Yeah. So when you are changing a variable that already has been created, as we did with the code that looked like this, you no longer need to remind the computer what the data type is. Thankfully, the computer's at least as smart as that. It will remember the type of the data that you intended. Other questions or comments on this? All right, that's quite a lot. Why don't we go ahead and here take a 10-minute break, and we'll be back. We'll start writing some code. All right. So we are back. We've just looked at some of the basics of compiling, even if it doesn't quite feel that basic. But now let's actually start focusing really on writing more and more code, more and more interesting code, kind of like we dove into Scratch last week. So here I have VS Code open. I've closed the GUI. I'm going to focus more on my terminal window and my code editors. Many different ways I can create new files, but I want to create something called a calculator. So again, within this environment of VS Code, I can literally write the code command, which is VS Code specific, and it just creates a new file for me automatically. Or I could do that in the GUI. I'm going to go ahead and create this file called calculator.c, and I'm going to go ahead and include some familiar things. So I'm just going to go ahead and proactively include CS50.exe, int.h, standard.io.h. I'm going to go ahead from memory and do the int void main. More on that next week, why it's int, why it's void, and so forth. And now let me just implement a very simple calculator. We saw like some mathematical operators like plus and the like, so let's actually use this. So let me go ahead and first give myself a variable called x, sort of like grade school math or algebra. Let me go ahead then and get an int, which is new, but I mentioned this exists. And then let me just ask the user for whatever their x value is. The thing in the quotes is just the English or the string that I'm printing on the screen, so I could say anything I want. I'm just going to say x colon to prompt the user accordingly. Now I'm going to go ahead and get another variable called y. I'm going to get int again, and now I'm going to prompt the user for y. And I'm just very nitpickily using a space just to like move the cursor so it doesn't look too messy on the screen. And then lastly, let me go ahead and just print out the sum of x and y. In an ideal world, I would just say something like printf x plus y. But that is not valid in C. The first argument, recall, in printf has to be a string in double quotes. So if I want to print out the value of an integer, I need to put something in quotes here, maybe followed by a new line if I want to move the cursor as well. So again, we only glimpsed it briefly, but what do I replace these question marks with if I want a placeholder for an integer? Yeah, so %i, right? Just like %s was string, %i is integer. So I change this to %i. And now if I want to add x and y, for instance, super simple calculator, doesn't do much of anything other than addition of two integers, I think this works. And again, it looks definitely cryptic at first glance. Like it would be nice if programming weren't this cryptic. Other languages will clean this up for us. But again, if you focus on the basics, printf takes one input first, which is a format string with English or whatever language, some placeholders maybe. Then it takes potentially more arguments after the comma, like the value of x plus y. All right, let me go ahead now and make calculator, which again compiles my source code in C, pictured above, and converts it into corresponding machine code or zeros and ones. No error messages, so that's already good. Now I do /calculator. Let's do 1 + 1 and enter. Voila. Now I have the makings of a calculator. Now let's start to tinker with this a little bit. What if I instead had done this? Int z gets x plus y, and then plug in z here. If I rerun make calculator, enter, rerun /calculator, type in 1 + 1, still equals 2, and let me claim that it will work for other values as well. Which of these versions is better designed? If both seem to be correct at very cursory glance, is this version better, or is the previous one without the z? OK, so this one's arguably better because I've now got a reusable variable called z that I can not only print, but heck, if my program's longer, I can use it elsewhere. Counter thoughts? Yeah, debatable like before because it depends on my intent. And honestly, I think a pretty good argument can be made for the first version because if I have no intention of, as you know, using that that variable again, you know what, maybe I might as well do this just because it's one less thing to think about. It's one less distraction. It's one less line of code to have to understand. It's just a little tighter. So here again, I think it does depend on your intention, but this feels pretty reasonable. And I think, as someone noted earlier, when I did the same thing with getString, that maybe kind of crossed the line because getString and the what's your name inside of it was just so much longer. But x plus y, it's not that hard to wrap our mind around what's going on inside of the printf argument. So again, these are the kinds of thoughts that hopefully you'll acquire the instinct for. Not necessarily reaching the same answer as someone else, but again, the thought process is what matters here. All right, so how might I enhance this program a little bit? Let's just talk about style for just a moment. So x and y, at least in this case, are pretty reasonable variable names. Why? Because like that's the go-to variable names in math when you're adding two things together. So x and y seem pretty reasonable. I could have done something like, well, maybe my first variable should be called first number, and my next variable should be called second number. And then down here, I would have to change this to first number plus second number. Like this isn't really adding anything semantically to help my comprehension, but that would be one other direction we could have taken things. So if you have very simple ideas that are conventionally expressed with common variable names like x and y, totally fine here. What if I want to annotate this program and remind myself what it is it does? Well, I can add in C what are called comments. With a // 2 forward slashes, you can write a note to yourself, like prompt user for x. And then down here, I could do something like prompt user for y, just to remind myself what I'm doing there. And down here, perform addition. Now, in this case, I'm not sure these comments are really adding all that much, because in the time it took me to write and eventually read these comments, I could have just read the 3 lines of code. But as our programs get more sophisticated and you start to learn more syntax that honestly you might forget the next day, the next week, the next month, it might be useful to have these sort of notes to self that remind you of what your code is doing, or maybe even how it is doing that thing. With these early programs, not really necessary, doesn't really add all that much to our comprehension, but it is a mechanism you have in place that can help you actually remind yourself or remind someone else what it is that's going on. Well, let me go ahead and rerun this again in this current version, make calculator. And here too, you might think I'm typing crazy fast. Not really. I'm hitting tab a lot. So it turns out that Linux, the operating system we're using here in the cloud, but actually Windows and macOS nowadays support this too, supports autocomplete. So if you only have one program that starts with CAL, you don't have to finish writing calculator. You can just hit tab, and the computer will finish your thought for you. The other thing you can do is if you hit up and keep going up, you'll scroll through your entire history of commands. So there too, I've been saving some keystrokes by hitting up quickly rather than retyping the same darn thing again and again. So again, just another little convenience to make programming and interacting with the command line interface even faster. All right, let me go ahead and just make sure it's compiled in the current form. The comments have no functional impact. These green things are just notes to self. Let me run calculator with maybe, how about this? Instead of 1 + 1, how about 1 billion? Let's see that again. 1 million, 1 billion, and another 1 billion. And that answer is 2 billion. All right, so that seems correct. Let's run this program one more time. How about 2 billion plus another 2 billion? Did you know that? So apparently it's not so correct, and clearly running 1 + 1 was not the most robust testing of my code here. What might have gone wrong? What might have gone wrong? Yeah. Yeah, the computer probably ran out of space with bits. So it turns out with these data types we've been talking about, string and int and also float and char and those other things, they all use a specific and most importantly finite number of bits to represent them. It can vary by computer. Newer computers use more bits. Older computers tend to use fewer bits. It's not necessarily standardized for all of these data types. But in this case, in this environment, it is using 32 bits for an integer. That's a lot. With 32 bits, you can count pretty high. This is 64 light bulbs on the stage and could count even higher. An int is only using half of these, or we have 2 integers here on the stage. Now, if you think back to last week, we talked about 8 bits at one point. And if you have 8 bits, 8 zeros and 1s, you can count as high as 256. Just a good number to generally remember as trivia. 8 bits gives you 256 permutations of zeros and 1s. 32 gives you roughly how many, if anyone knows? It's 2 to the 32 power. So it's roughly 4 billion, 2 to the 32. If you don't know that, it's fine. Most programmers will eventually remember these kinds of heuristics. So it's roughly 4 billion. So that feels like enough. 2 billion plus 2 billion is exactly 4 billion. And that actually should fit in a 32-bit integer. The catch is that my Mac, your PC, and the like also like to support negative numbers. And if you want to support both positive and negative numbers, that technically means with 32-bit integers, you can count as high as roughly 2 billion positive or 2 billion negative in the other direction. That's still 4 billion, give or take, but it's only half as many in one direction or the other. So how could I go about implementing a correct calculator here? What might the solution be? Yeah, so not just li, which was for long integer. I have to make one more change, which is to the data type itself. So let me go back up here and change x from an int to a long, aka long integer. And then let me change y as well. And then let me change the format code per the little cheat sheet we had up a few minutes ago to li. Let me recompile the calculator. Seems to work OK. Let's rerun it. Now let's do 1 + 1. That should obviously be the same. Now let's do 2 billion. And another 2 billion, and cross our fingers this time. Now we're counting as high as 4 billion. And we can go way higher than 4 billion, but we're only kicking the can down the street a bit. Even though we're now using, with a long, 64 bits, which is as long as this stage now, that's still a finite value. It might be a really big value, but it's still finite. And we'll come back at the end of today to these kinds of fundamental limitations, because arguably now, my calculator is correct for like millions, billions of possible inputs, but not all. And that's problematic if you actually want to use my calculator for any possible inputs, not just ones that are roughly less than, say, 2 billion, as in this case. All right, any questions then on that? But it's really just a precursor for all the problems that we're going to have to eventually deal with later on. A good question. Yes, if we were still using z, we would also have to change it to a long. Otherwise, we'd be ignoring 32 of the bits that had been added together via the longs. Good question. All right, so how about we spice things up with maybe not just addition here. How about something with some conditions? Let's start to ask some actual questions. So a moment ago, recall that we had just the declaration of variables. Now let's look back at something in Scratch that looked a little something like this. A bunch of puzzle pieces asking questions by way of these conditionals, and then these Boolean expressions here in green, maybe saying something like x is less than y. In C, this actually maps pretty cleanly. It's much cleaner from left to right than it was with printf and join. Here we have just code that looks like this. If, a space, 2 parentheses, and then x less than y, and then we have something like printf there in the middle. So here it's actually kind of a nice mapping. Notice that just as the yellow puzzle piece in Scratch is kind of hugging the purple puzzle piece, that's effectively the role that these curly braces are playing. They're sort of encapsulating all of the code on the inside. The parentheses represent the Boolean expression that needs to be asked and answered to decide whether or not to do this thing. And here's an exception to what I alluded to earlier. Usually, when you see a word and then a parenthesis, something, and then close parenthesis, I claim that's usually a function. And I still feel pretty good about that claim. But there are exceptions. And the word if is not a function. It's just a programming construct. It's a feature of the C language that similarly uses parentheses just for different purposes, for a Boolean expression. How about something like this? Last week, if you wanted to have a two-way fork in the road, go this way or that way, you can have if and else. In C, that would look a little something like this. And if we add in the printfs, it now looks quite like the same, but it adds, of course, the word else and then a couple of more curly braces. As an aside, in C, it's not strictly necessary to have curly braces if you have only one line of code indented underneath. For best practice, though, do so anyway, because it makes super clear to you and ultimately anyone else reading your code that you intend for just that one or more line of code to execute. How about this from last week? Here was a three-way fork in the road. If x is less than y, else if x is greater than y, else if x equals y. Now here's where you have some disparities between Scratch and C. Scratch uses an equal sign for equality, to compare two values. C uses a single equal sign for assignment, from right to left, minor difference between the two worlds. In C, we could implement the same code like this, the addition being just this additional else if, and if we add in the printfs, it looks a little something now like this. This is correct, both in the Scratch world and in the C world, but could someone make a claim that this is not, again, well designed? Exactly. We don't need the last if. We need the else at least, but we don't need the last if because at least in the world of comparing integers, it's either going to be less than, greater than, or equal to. There is no other case. So you can save a few seconds, if you will, of your program running, a blink of the eye, by only asking 2 questions and then inferring what the answer to the third must be just by nature of your own human logic here. Now, why is that a good thing? If, for instance, x and y happen to equal each other, I type in 1 and 1 for both values, either in Scratch or in the C world. In the case of this version, you're sort of stupidly asking 3 questions, all of which are going to get asked, even though the answer is no, no, yes. That is true, false, false, true. That seems to be unnecessary because if we instead optimize this code, get rid of the unnecessary if, and just do as you propose logically, else print that x is equal to y. Now, if x indeed equals y, because they're both 1 or some other value, now you're only going to ask 2 questions, so 2/3 as many questions, and then you're going to get your same correct result. So again, a minor detail, but again, the kinds of things you should be thinking about, not only as you write your code to be correct, but also write it to be well designed as well. All right, so why don't we go ahead and translate this into the context of an actual program here. I'll create a blank window here, and let's do something with like points on my own very first CS50 problem set. Let me go ahead and run code of points.c. That's just going to give me a new text file. And then up here, I'm going to do my usual, include CS50.h, include standard.io.h, int main void. So a lot of boilerplate, so to speak, in these early programs. And now let's ask the user how many points did they lose on their most recent CS50 p set to sort of evoke my photograph of my own very first p set last week where I lost a couple of points myself. So int points equals get int. Then I'll ask a question in English like, how many points did you lose? Question mark space. And then, once I have this answer, let's now ask some questions of it. So if points is less than 2, borrowing the syntax that we saw on the screen a moment ago, let's go ahead and print out something explanatory like, you lost fewer points than me, \n. All right, else if points greater than 2, which is, again, how many I lost, I'm going to go ahead and print out, you lost more points than me, \n. Else if, wait a minute, else seems to be sufficient logically here. I'm just going to go ahead and print out something like, you lost the same number of points as me, \n. So really just a straightforward application of that simple idea, but to like a concrete scenario here. So let me go ahead and save this. Let me go ahead and run make points, enter. No errors, that's good. Run points, and then how many points did you lose? How about it's 1 point? All right, you lost fewer points than me. How about 0 points? Even better. How about 3 points? And so forth. So again, we have the ability to express in C now, pretty basic idea from last week in reality, which is this notion of conditionals and asking questions. There's something subtle here, though, that's maybe not super well designed, that someone might call a magic number. This is sort of programming speak for something I've done here. There's a bit of redundancy, unrelated to the if and the else if and the else. But is there something I typed twice, just to ask perhaps for the obvious? Exactly. I've hard-coded, so to speak, manually typed out the number 2 in 2 locations in this case that did not come from the user. So this is apparently, once I compile this is it. You're always comparing yourself to me in like 1996, which for better or for worse is all the program can do. But this is an example, too, of a magic number in the sense like, wait, where did that 2 come from, and why is it in 2 places? It feels like we are setting the stage for just a higher probability of screwing up down the road. Because the longer this code gets, suppose I'm comparing against 2 points elsewhere, 2, 3, 4, 5 places. Am I going to keep typing the number 2? Like, yeah, that's fine. It's correct. It's going to work. But honestly, eventually, you're going to screw up, and you're going to miss one of the 2s. You're going to change it to a 3 because maybe I did worse the next year, or 1, I did better. And you don't want these numbers to get out of sync. So what would be like a logical improvement to this design, rather than hard coding the same number sort of magically in 2 or more places? Yeah, why don't I make a variable that I can use in there? So for instance, I could create a variable like this, another integer called mine, and I'm just going to initialize it to 2, and then I'm going to change mentions of 2 to this. And mine is a pretty reasonable name for a variable insofar as it refers to exactly whose points are in question. There's a risk here, though, minor though it is. I could accidentally change mine at some point. Maybe I forget what mine represents, and I do some addition or subtraction. So there's a way to tell the computer, don't trust me, because I'm going to screw up eventually, by making a variable constant, too. So a constant in a programming language, this did not exist in Scratch, is just an additional hint to the computer that essentially enables you to program more defensively. If you don't trust yourself necessarily to not screw up later, or honestly in practice, if you know that number should never change, make it constant and never think about it again. This tells the compiler to make sure that even you, later in your code, cannot change the number 2. And another convention in C and other languages, when you have a constant, it's often common to just capitalize the variable. Kind of like you're yelling, but it really just visually makes it stand out. So it's kind of like a nice rule of thumb that helps you realize, oh, that must be a constant. Capitalization alone does not make it constant. The word const does, but the capitalization is just a visual reminder that this is somewhere, somehow, a constant. So just a minor refinement, but again, we're sort of getting better at programming just by sort of instilling these kinds of heuristics. Questions then on conditionals in C or these constants? Yeah. Yeah, why do you not use a semicolon in like lines 9, 13? No good, just because. Like, this is the way the language was designed, and it's confusing early on. Generally speaking, when you're using conditionals, and eventually we'll see loops, there's no semicolons involved. For now, assume that semicolons usually finish your thought after a function. That's not 100% reliable of a heuristic, but it'll get you most of the way there. And just because. Left hand was not talking to right hand when some of these languages were designed. All right, so let's do something else. How about this? if I have the ability to ask something conditionally, is this thing true or is this other thing, could I write a very simple program that does something basic like tells me if a number the human types is even or odd? Well, let me just get the framework for that in place. Let me go ahead and write code of parity as a fancy way of saying even or odd. And let me go ahead and include CS50.h, include standard IO.h, int main void. Again, more on those down the road. But for now, I'm going to go ahead and get a number, n, from the user by calling getInt and asking them for whatever n is. And then now I'm going to introduce some pseudocode. So here's the first example of a program, honestly, that I'm not really sure how to proceed. So let me just resort to some pseudocode using comments. Eventually, I'll get rid of this and write actual code. But if n is even, then print. Actually, let me just print that. Let me just go ahead and say printf, quote unquote, even, because I know how to use printf. Else, all right, I know how to printf odd, so let me just say printf, quote unquote, odd. So here, I've sort of taken a bite out of the problem, if you will. And let me go ahead and put in my little placeholders. I want to do some kind of condition. So if question marks now, let me go ahead and fill in the blanks here. Else, I'll put this here. So I think I'm OK now. I'm getting closer to solving this, but I still have this question mark here. How, using syntax we've seen, might I determine if n is even or odd? What do you think? Nice. There's this little operator I mentioned by name earlier, the remainder operator, that will let you do exactly that. If you divide any number by 2, that mathematical heuristic is going to tell you if it's even or odd based on whether there's a remainder of 0 or 1. And that's nice because the alternative would seem to be doing something stupid like if n equals 0 or n equals if n equals 2 or n equals 4. Right? Your code would be infinitely long if you had to ask all possible questions. But if I do n divided by 2 and look at the remainder, it's a little cryptic, but this will indeed do the trick. So the percent sign is the remainder operator. It does numerator divided by denominator and returns not the result of that, but rather the remainder of that. So if you divide anything by 2, it's going to be a 0 or 1 remainder. And if indeed 2 divides into n evenly, giving you 0, then you're going to print even, else it's got to be odd. But there is something odd, pun intended, in this highlighted line. What is another new piece of syntax, apparently, besides the percent sign? What's a little off there? Yeah. Yeah, so that's not a typo. And I even caught myself verbally saying it a moment ago just because it's so ingrained. What must this mean here? Yeah. Yeah, if something's equivalent to the other. So now this is the equality operator. It's not assignment from right to left. And this one, too, is an example of like literally humans not really planning ahead, perhaps. Left hand not talking to right hand, and that someone decided, let's use the equal sign for assignment. And then some number of minutes or days later, people are like, damn, how do we now compare for equality? Well, let's just use 2. And if you think this is a little weird, in some languages like JavaScript, there's a third version where you use 3 equal signs. So again, it's humans that design these languages. So if you're ever frustrated by them, confused by them, admittedly, it might just not have been the best design. But we just kind of have to live with it ever since. So let me go ahead and zoom out here. Let me go ahead and make parity here. So make parity, and again, parity is just the name of my file, parity.c, /parity, type in a number like 2. That's indeed even. 4. That's indeed even. 3. That's indeed odd, and so forth. If we continue testing, presumably we'll get the same kinds of answers. How about something else? Let me go ahead now, and let me start copying and pasting some of this code, because admittedly, it's getting a little tedious to keep typing out all of that boilerplate at the top. Let me create a program called agree.c that's reminiscent of like any of those forms you have to agree to online with a checkbox or typing in yes or no or the like. So let me throw away all the guts of this main program, and now ask something like this. Let me go ahead and prompt user to agree to something. I'm going to go ahead ahead and say, how about get string, do you agree, whatever the question might be, and I want the human to type y or no, y or n for yes or no respectively. So if it's only a single character, actually, I can actually get by with just get char. Not used it before, but it was on our menu of functions from the CS50 library. And if I want to get the user's response, the return value should be a char also on the left. So now we've seen strings, ints, and now chars if we only care about a single letter. And now let's go ahead, check whether user agreed. So how about if c equals quote unquote y, then let me go ahead and inside of my curly braces print out agreed, or some such sentence like that. Else, if they did not type C, or you know what, let's be explicit here, just so they can't type Z or B or some random letter. Else, if C equals quote unquote N for no, then let me go ahead and print out not agreed, or something like that. And I'm just going to ignore the user if they don't cooperate and they type Z or B or something that's not Y or N. All right, let me go ahead now and compile this code, make agree, /agree. All right, do I agree? Yes, let's go with the default. OK, so that seems to work. No, I don't agree this time. That seems to work. How about my caps lock key is on, or I'm just really yelling, capital Y, it ignores me. Capital N, it ignores me. So obviously a bug, at least if I want to tolerate uppercase and lowercase, which is kind of reasonable. So what would be the possible solutions here, do you think? How do I solve this and tolerate both capital and lowercase? Maybe what's the simplest, most naive implementation? Yeah, so why not just ask two questions? Or you know what, even more simplistic, based only on what we've seen before. Let me, if you will, let me just kind of copy and paste some of this code, change this to an else, whoops, not in caps, else if, quote unquote capital Y, and then I bet I could do the same thing with n. But here too, just like with Scratch, as soon as you start to find yourself copy pasting, you're probably doing something wrong. And what you said verbally, if I may, was actually better because you're implying that I could just say something like or C equals capital Y, or down here C equals capital N. The catch is you can't use the word or in C. It's actually two vertical bars. So you can express one question or another. You only need one of the answers to be yes or true, and you use two vertical bars. By contrast, just so you've seen it, if you wanted to check if something is equal to something and something else, you could use two ampersands. This logically would make no sense here, though. Certainly, what the human types can't both be lowercase and uppercase. That just makes no sense. So in this case, we do want or, but that allows me to tighten my code up. I don't have to start copying and pasting whole branches. I can now ask two questions at once. Questions, then, on this variation. Really good question. Can you convert the input to all lowercase? Absolutely, you could. We don't have the capability yet. It turns out that's going to require, to be easy, another library that we could do it ourselves, knowing a little bit about ASCII or Unicode from last week. But yes, that would be an alternative, but more on that a different time. Other questions? Good question. Unfortunately, you have to be explicit in C. You can't just say this, even though that's kind of how you might think about it. You have to ask a complete question using the equality sign twice in this case. Let me ask you a question now, too. It's not a typo. I deliberately used single quotes around all of my single letters here. Why might that be? Previously, we used double quotes for anything that looks like text. Yeah. Correct. String is double quotes for multiple characters, or even one technically, but yes. And single quotes for single characters. Because my data type is different, I chose the simple route of just using a single char. In fact, this program won't work with YES or NO. That's not supported at the moment. More on that another time. I had to use single quotes because that's how C does it. If you're dealing with single characters, aka chars, use single quotes. If it's a string, even if it's one single character in a string, as though you're starting to write out a longer word or sentence, that would be double quotes. And we'll see why this is before long, too. But again, just sort of things to keep in mind whenever writing code in this particular language. Yeah, down here. So short answer, if I'm understanding correctly, this would be incorrect. And this would be even more incorrect. But if you don't mind, let me kick the can a couple of weeks on this as to why this doesn't work. The most pleasant way to do this would indeed be to do something like this. But even this is a slippery slope, because what if the user does something weird, like they capitalize just the Y? You can imagine this getting messy quickly. I like your idea earlier about just forcing everything to lowercase, just to standardize things. Unfortunately, you cannot compare strings for equality like this, for, again, reasons we'll come to before long. So for today, we're keeping it simple, even though arguably it's not nearly as user-friendly to only tolerate individual letters. And there's a question over here. On a US English keyboard, it's Shift and then the / key above return. But depending on your keyboard, it will vary. All right, so let's actually now look back at something we did a little bit of last week. Let me go ahead and open a file called meow.c, because recall that's what we had Scratch do initially. Let me include not the CS50 library this time, but just standard io.h, because I only want printf for this demo. Let me go ahead now and just print out meow. And then if I want the cat to meow 3 times like it did last week, meow, meow, meow. Save it, make meow, /meow, voila. Program is written. Correct, I claim. It ran, it compiled OK. But again, this was the beginning of our conversation last week of not being particularly well designed. And if someone wants to maybe point out the now obvious, like why is this not well designed necessarily? Yeah, it's just repetition, right? Again, I literally resorted to copy-paste. Like, that should be the signal that you're probably doing something wrong, or at best, just lazy of you in this case. So the solution, as you might glean from last week, is probably going to be one of those things called loops. So let's just take a look at some of the syntax for loops in C. But again, no new ideas. It's just some new syntax that'll take some getting used to. In Scratch, if you wanted to meow forever with something like this, there's not a forever keyword in C. So this one's a little weird to look at, but this is the best we can do. It turns out there is a keyword called while. in C. And that kind of has the right semantics, because it's like while, like do something again and again. That's the best I can do. But just like an if condition or an else if condition, those took a Boolean expression in parentheses. A while loop also takes a Boolean expression in parentheses. So I have to ask a question. Now, if I want to do something forever, I could kind of stupidly just say while 2 is greater than 1, while 3 is greater than 2, or just something completely arbitrary. But that should rub you the wrong way, because like why 2 versus 1, why 3, like just if you want true, just say true. So it turns out in C, there are special keywords, true and false, that are literally true and false respectively. I could also put the number 1 for true and the number 0 for false, but most people would just say true to be explicit. So it's a little hackish, if you will, but very conventional. There's no forever keyword in C. If I want to then print meow forever, I'm going to just use something like printf here. So again, not perfect translation from one to the other, but absolutely possible in C. What about this? This is a little more common if you want to do something a finite number of times, like repeat 3. There's a few different ways we can do this in C. Here's one I would approach. And here's where C, like a lot of text-based languages, you kind of have to whip out that toolkit of all of the basic building blocks and think about, all right, how can I build a little machine in software that does something some number of times? Well, let me give myself a variable called counter, set it equal to 0. Let me create a loop whose Boolean expression is counter less than 3. The idea being here, why don't I just kind of count 1, 2, 3? So how do I implement this physicality in code? I give myself a variable, set it to 0, 0 fingers up. Now I ask the question, is counter less than 3? If so, go ahead and print out meow. And just intuitively, even if you've never seen C code or any code before scratch, what more do I need to do? I've left room here for one more line of logic. Yeah. We have to increase counter. So I need code like I showed earlier, like counter equals counter plus 1. And so here's where like programming sometimes becomes a bit more like plumbing. Like you can't just say what you mean like you could in Scratch. You have to build a little sort of software machine that initializes a value, does something, increments it, checks it. And so it's kind of like this software-based machine, but together that's just using some familiar building blocks. But this is pretty common. Just like in Scratch, you might have used loops a bunch of times. Pretty common in C. So can we tighten this code up? This is correct, but here's some conventions that are popular. You know, if you're going to count, just say I. A convention in programming with at least languages like C is just use I as an integer if all its purpose is to count from like 0 on up. Counter's not wrong. It's not bad. It's just like it's more verbose than you need to be. Just call it I. You don't need more semantics than that. All right, what else can I do here? There's another opportunity to tighten up this code. Do you recall? Yeah. Yeah, that syntactic sugar that does nothing new, but it does it more succinctly. I can change this to either the intermediate format or the even tighter format of just I++. Now, this is pretty canonical. Like, this is how most people would implement something 3 times using a loop in C, using a while loop, that is. Turns out that it's so common in C and other languages to do something finitely many times, there's a couple of ways to do it. In this model, to be clear, the logic, though, is that we start by initializing the variable, like I've highlighted here. We then ask the question, is I less than 0? If so, everything that's indented inside the curly braces gets executed, namely meow, then the update. Then the computer is going to have to recheck the condition to make sure that I hasn't gotten so big that it's greater than 3. But if not, it then does this again, and it does this again. And then it repeats, constantly checking the condition and executing what's in the block, checking the condition and executing what's in the block. After 3 times of that, the condition is going to be false or a no answer, and that's it for the code. It just proceeds to whatever's down here, just like with Scratch. It jumps to the next blocks down below. All right, what's another way, though, to do this? Well, I've deliberately been counting from 0, and that's a programming convention, right? We started last week with all the light bulbs off, which was 0. So it's pretty reasonable to start counting at zeros, just like you would here, like no fingers are up. This is 0, fingers on your hand. But if you prefer, you could start counting at I equals 1. But then you don't want to do it while I is less than 3. You want to do I is less than or equal to 3. On most keyboards, there's no symbol for less than or equal to or greater than or equal to. So in C, you use 2 characters, less than and then an equal sign with no spaces in between. That just means less than or equal to. We could change it to set I to 2 and make this condition be less than or equal to 4. We could make this be 10 and less than or equal to 12. But again, just stick with the basics. Start at 0 and count on up would be the convention. Or if you prefer to count down, that's fine too. Set I to 3. And then do this so long as I is greater than 0, but you have to decrement instead of increment. So again, we could do this all day long. There's like literally an infinite number of ways to implement this idea, and that's why I keep emphasizing convention. Call the variable I for something like this, initialize it to 0 for something like this, and just generally count up unless you really prefer to count down. Again, just certain human conventions. All right, how about another way to do this? This is what's called a for loop in C. Also very common. It's not quite as straightforward in that it doesn't really read top to bottom in exactly the same way. This kind of has a lot more logic tucked into its first line, but it does exactly the same thing. What happens here is, notice that inside the parentheses, next to the word for, there's 2 semicolons, which is another weird use of syntax. They're not at the end of the line. Now they're in the middle of the parentheses, but that's what the humans chose years ago. The first thing, before the semicolons, initializes your variable, int I equals 0. The next thing is the condition that's going to constantly get checked every cycle through this loop. And the last thing is going to be what you do after each loop, which in this case is going to be count up. So again, if I rewind, we initialize I to 0. We then ask the question, is I less than 3? If so, execute what's inside of the loop. Then the computer does this. It does the update, incrementing I by 1. And then it's not going to blindly meow again. It's going to check again the condition is I less than 3. Then it's going to meow if so. Then it might go ahead and increment I and check the condition again. So again, this does not read quite in the same simple fashion top to bottom. You kind of read it left to right and then jump around. But again, the initialization, the constant Boolean expression being checked, and the update after each time. Does the exact same thing as what we saw a moment ago in this while loop formats. Which one is better? They're the same. I think most people would probably eventually use a for loop once comfortable, but just because is really the answer there. All right, any questions then on loops as we translated them to C? Yeah? For loop and while loop can both be used to do exactly the same thing. There are subtle differences with issues of scope, which we'll discuss before long, where when you create a variable in a for loop, notice that it was, again, inside of those parentheses, which technically means it's only going to exist in these 4 lines of code. By contrast, with the while loop, I declared my variable outside of the loop. That variable is going to continue to exist elsewhere in my program. So that's one of the minor differences there. Good question, but you'll see some others over time. All right, so we claim then that it's better in some form to do this with loops. So let's actually jump back to the code. Let me go ahead and now re-implement meowing with a for loop, for instance. So how about for int I gets 0, I less than 3, I less than 3, I plus plus. Then inside my curly braces, let me go ahead and print out with printf meow with a new line and a semicolon. So I did it pretty quickly just because I've long acquired the muscle memory. But if I now make meow, no errors there, run /meow, and I see meow, meow, meow. Well, let's do now what we did last week, which was to begin to make our own custom functions, if you will, by using our own in C. So here's where the syntax gets a little funky, but we'll explain over time what each of these keywords is doing. If I want to create a function called meow, because the authors of C did not create a function called meow decades ago, I need to give it a name, like meow. I need to specify if it takes any inputs. For now, I'm going to say no. And I'm going to explicitly say no by writing the special word void. It's also necessary when implementing a function in C, which was not necessary in Scratch, to specify what its return type is. But for now, I'm just going to say that meow is the name of the function. It takes no inputs, and that's what the void in parentheses means. And it does not return anything like ask did, or like getString, or getInt does. Meow's purpose in life is just to have side effects, visual side effects by printing something on the screen. So what is meow going to do? I'm going to have it quite simply say printf quote unquote meow \n. And now, just like in Scratch, I can now just call a brand new function called meow. And here's where, too, if you really don't like the curly braces, technically speaking, you can get rid of them when there's only one line of code inside your loop. But again, stylistically, I would encourage you to preserve them to make super clear to yourself and others what it is that's going on. Let me go ahead and save this and do make meow. Whoops. Darn. All right, what did I do? Something stupid? Yeah, so 0 does not belong there. I meant to hit parenthesis. So let me rerun make meow. OK, fixed. My mistake. All right, it's still working OK. But recall what I did in Scratch, kind of out of sight, out of mind. And just to make a point, let me just kind of highlight this and move it way down in the file. Because again, like now that meow exists, it's an abstraction. I just know a meow function exists. I want to be able to use it. So let me scroll back up. My main function is the same. Let me go ahead and make meow again. And now just by moving that function, I've created all these lines of errors. And let's look at the first. Again, the rule of thumb here, it's a little small, but it says meow.c in bold, which is the name of the file where the bug is. 5 is the line number, and 20 is the character. So line number is enough alone. Let's see. Oh. This is what happens when I scrolled up too far. Sorry, this is the error we're now looking at, line 7. I was looking at the old error message from earlier before I fixed the 0. Meow C, line 7. All right, apparently C does not know what the meow function is. Implicit declaration of function meow is invalid in C99. Well, what does that mean? Declaration of function means your creation of a function. Like I'm declaring that meow exists, but I haven't apparently defined it yet. And then C99 is a version of C from the year 1999, which we generally use here. It's one of the more recent versions. So why is that the case? Can you infer from the mere fact that I just moved meow to the bottom of the file, which was fine in Scratch, but now is bad? Why is that? Yeah, C is just kind of old school. It reads your code top to bottom, and if it does not know what meow is when you first try to use it, it just freaks out and prints out these error messages. So the solution is quite simply, don't do that. Just leave it where it was. But you can imagine this getting a little annoying over time, if only because main is by name the main part of your program. And honestly, it would just be nice, honestly, if main were always at the top of your code, because if you want to understand what a file is doing, it makes sense to just read it top to bottom. Well, there is a solution to this. You can put functions in different orders with main at the top, so long as you, and this is perhaps the only time copy-paste is appropriate, so long as you leave a little breadcrumb for the compiler at the very top of your file that literally repeats the return value, the name, and the arguments to that function, semicolon. This is, so to speak, declaring your function. And the real fancy way is this is a prototype. It's like, what is this thing going to look like? But the semicolon means I'm not going to deal with this yet. I'm going to actually define the function or implement it down below here. This is kind of a stupid detail. More recent languages get rid of this need. You can put your functions in any order. But again, if you just think about the basics of programming languages like this one here, and as you noted, it must just be reading your code top to bottom. So annoying, yes, but explained, yes, too. So let me go ahead and make meow once more time. /meow, still working OK. And let me make one final enhancement to this meow program here. Let me go ahead now and say something like this. Let me go ahead and say, all right, wouldn't it be nice if my meow function could do something for me some number of times? So suppose I want to do this. This meow function at the moment is going to meow 3 times. But suppose I want to meow n times, where n is just some number provided by the user. Well, just like in Scratch, custom functions can take inputs. I just presently am saying void. But if I change this to int n, thereby telling the compiler, hey, meow still doesn't return something, but it does take something as input. It takes an integer, and I want to call it n. So this is another way of declaring a variable, but a way of declaring a variable that gets handed into as input the function. So now if I tighten up main here, now I can actually do something really cool, just like in Scratch, which is this. if I now look at this code, let me zoom in here. Now my main program is really well written in the sense that it just says what it does, meow 3 times. This works, though, because I define meow as now taking an input, an integer called n, and then using n in my now familiar for loop. There's one change. You might have caught my one mistake. I also have to remind myself up here to make that change too. Again, this is one of the only redundancies or copy-paste that's sort of reasonable. But there I have now a better version. So let me go ahead and rerun this. Make meow, dot slash meow, voila. So again, no change in correctness, but now again, we're sort of modularizing our code. And heck, what you could do now, and this is just a tease of a feature down the road, those header files we talked about earlier, those libraries, this is the kind of modularization we're talking about. We, the staff, wrote a function called getString, getInt, and so forth. We put it in a file called CS50.c, and we put little breadcrumbs, specifically these things called prototypes, in CS50.h. So that when you all, as aspiring programmers, include CS50.h, you are sort of secretly telling the compiler at the very top of your code what the menu of available functions is. Why? Because in CS50.h is lines like these. Obviously not for meow, but for getString, getInt, and so forth. And in standard IO.h is the same lines of code for things like printf. So that's all that's going on there. It's just a way of telling the computer in advance what functions to expect. Are any questions then on these here? Correct. So if you don't mind, I want to continue to wave my hand at that detail for today. Indeed, int main void is a little weird because, like, what would the input to main be? We have no mechanism for providing input yet. And what does it mean for main to return anything? Like, who is it returning to? For another day, if we may. They're going to come into play, but that for now today is just something you should take at face value as necessary copy-paste to begin programs. So meow is a function that takes an input, the number of times to meow, but it didn't actually have a return value, hence the void. But what if we actually want to create our own function that not only takes 0 or more inputs as arguments, but also returns some value, maybe an int, maybe a float, maybe something else altogether? Well, it turns out in C, we can do that as well. Let me go ahead and create a new file here called discount. And let's implement a quick program via which we can discount some regular price by some percentage, as though there's a sale going on in a store. Let me go ahead and include our usual CS50.h, followed by standard IO at the top. Let me give myself int main void, as before. And inside of main, let's go ahead and do something simple. Let's give ourselves a float called regular, representing like the regular price of something in a store. Let's go ahead and get a float from the user, asking them what that regular price is. Then next, let's go ahead and declare a second variable, also a float, called sale, ultimately representing the sale price after some percentage discount off. And let's go ahead and simply calculate whatever regular is and say 15% off is a pretty good discount. So let's go ahead and discount regular, whatever it is, by 15%, which is equivalent, of course, to multiplying it with the asterisk by 0.85. Of course, if we're taking off 15%, we multiply the regular price by 0.85. Now let's go ahead and print out the results here. Let me go ahead and say printf. Sale price, colon. Let me go ahead and use %f, but more specifically %.2f, because at least in US currency, we typically show cents to 2 decimal places, followed by a new line. And then let me go ahead and plug in the value of sale. All right, let's go down here and do make discount. Enter. So far, so good. /discount. And the regular price is maybe $100. So the sale price should be $85. So our arithmetic seems to be correct here. But let's fast forward now in time. Suppose that we find ourselves discounting a lot of prices in an application, maybe a website like Amazon where they're offering some kind of percentage discount. It'd be nice to have a reusable function that just does this arithmetic for us, simple though it may be. So let's go ahead and modify discount this time to give ourselves our own function called discount, for instance, that takes an input, like the regular price that you want to discount, and then it also returns a value. It doesn't just print it out. It returns a value, namely a float that represents what the sale price is. So let me go down below main and go ahead and define a function that's going to return a float, because we're dealing with dollar amount still. The function is going to be called discount, and it's going to take one input, like the price that we want to discount. In here, I'm going to do something very simple. I'm going to say float sale equals whatever that price is times 0.85, and then I'm going to go ahead and return sale. Now, for that matter, I can actually tighten this up a bit. If I'm only declaring a variable to store a value that I'm then returning with this keyword return, I actually don't even need that variable, so I can delete the second line, and I can actually just go ahead and get rid of that variable altogether and immediately return whatever the arithmetic result is of taking the price input, the argument that's being passed in, times 0.85. So a very simple function that simply does the discounting for me. As always, let me go ahead and copy paste, almost the only time it's OK to copy paste, the prototype of that function to the top of the file so that when compiling this code, main has already seen the word discount before. And now let me go into the code here, and instead of doing the math myself in main, let me presume that we have some function already in our toolkit called discount that lets me discount the regular price and return that value. And then down here, my code doesn't need to change. I'm still going to print out sale, the variable in which I'm storing that result. But notice what I've done here. I've sort of abstracted away the notion of taking a discount by creating my own function that takes a float called price or anything else as input. It does a little bit of math, simple though it is here, and then it returns a value. But notice the discount is not printing that value. It's literally using this other keyword called return so that I can hand back that value, just like getString hands back a value, just like getInt hands back an integer without printing it for you, so that I, up here on line 9, can go ahead and store that value in a variable if I want, and then actually print it out. Let me go ahead now and recompile this code with make discount. Let me go ahead and do /discount. And let's, again, do $100. Sale price is going to be 0.85. $5 as well. Now, it turns out that functions don't have to take just 0 or 1 argument as input. They can actually take 2 or 3 or more. So in fact, suppose we wanted to now enhance this version of my program and take in as input to the discount function not just the price that I want to discount, but also the percentage off, thereby allowing us to support not just 15% off, but any number of percentage points off. Well, let me go up here and declare an int say and call it %off. And let me ask the user for how many percentage points they want to take off. So I'm going to say %off inside of the props here, get that int called %off. And now, in addition to passing in regular as an input to the discount function, I'm also going to pass in %off. But I need to tell the computer that it is taking now 2 arguments, and the way I do this is just with a comma down here in the function's own definition. Here is going to be a percentage argument, a second argument per the comma, and I'm now going to use that percentage in a slightly familiar way. I don't want to just do percentage like this, because of course that's going to increase the size of the total price. I actually need to do a little bit of real-world math, where if this is a percentage off, like the number 15 for 15 percentage points, I need to do like 100 minus that many percentage points, thereby giving me 100 minus 15, 85. And then I need to divide that by 100 in order now to give myself 0.85 times the price that was passed in. But if I go ahead now and save this, run, make discount one last time, I notice that I've actually got an error here. What have I done wrong? Well, I need to change that prototype too. And again, this is admittedly an annoying aspect of C that you have to maintain consistency here, but that's fine. I'm just going to go up here, change this to int percentage, spelling incorrectly, and now let me retry compilation, make discount, crossing my fingers this time, worked OK, /discount, and voila, $100, and %off, say 15 points, and voila, $85. Now, it's worth noting that I've deliberately returned the results of my math from this function. I haven't just done the math on the original variable that's being passed in. In fact, if we take a look at this second version, where discount is now taking a price argument and a percentage argument, notice that I'm not doing something like this. I'm not just saying price equals price times 100 minus percentage divided by 100 and leaving it at that. The problem there is that this variable price is going to be scoped to that discount function. And we'll encounter this again before long, but this notion of scope just refers to where in which a variable actually lives or exists or is accessible. So it turns out if I change price in the context of this discount function, that's not going to have a lasting effect. If I actually want to get the result back to the function that used the discount function, namely main, I actually do need to take this approach of actually returning the value explicitly so that ultimately I'm handing back the discounted price. All right, well, let's go ahead and maybe, how about let's just use these primitives in just a few different ways. How about a little game of yesteryear, Super Mario Brothers. And in the original Super Mario Brothers, and in bunches of variants in, so you have like these side-scrolling worlds that look like this, where there's some coins in the sky hidden behind these question marks. So let's just use this as a visual to consider how, in C, could I start to make something semi-graphical? Like not actual colors or fanciness, that feels like too much too soon, just something like printing out some question marks. Well, if I go back over here, let me create that actual file that I alluded to earlier. So let me code up mario.c. Let me go ahead and include standard io.h, int main void, again, which we'll continue to copy paste for today. And then let me just go ahead and do something simple like 1, 2, 3, 4, and a new line. All right, this is what we might call ASCII art, which just means graphics, but really just implemented with your keyboard. And if I make Mario and do /Mario, it's not nearly as engaging visually as this, but it's the beginning of this kind of map for a game. Well, if I wanted to now print out of those things dynamically, let me go back to my code here. And instead of printing out 4 all at once, I could do something like for int I get 0, I less than 4, I plus plus. And then inside here, I could just print out one of them at a time. Let me save that. Make Mario, and at the risk of disappointing, so close, but I made a mistake. Just stupid aesthetic. The prompt is not on the new line. How could I move it? Yeah, I need an escape character, the \n, but should I put it here? OK, no, because that's going to put it after everyone, and it's going to make this thing vertical instead of horizontal. So logically, just like in Scratch, put it at the end of the loop. So something out here, and just print out, for instance, only quote-unquote new line. And now if I do make Mario again, /Mario, OK, we're back in business. But a little better designed in that now I'm not repeating myself multiple times. I'm doing this again and again. But let's do one other thing here with Mario. Let me go ahead and ask the user how many question marks or coins to print. The catch here is that there's another type of loop that's helpful for this, and it's called a do-while loop generally. A do-while loop is similar to a while loop, but it checks the condition last instead of first. Recall earlier on the slide, we had while, open parenthesis, close parenthesis, and I kept claiming that we checked whether I is less than whatever it was, 3 in advance, again and again. A do-while loop just inverts the logic so that you can actually do something like this. At the top of this program, I'm going to go ahead now and give myself a variable n, like this, type integer, and then I'm going to do literally the following with the keyword do. N equals get int, and I'm going to ask the user for the width, like the number of $signs to print. And I'm going to do this while n is less than, say, 1. So this is a little cryptic, but the salient differences are the Boolean expression is now at the bottom of my block of code, not at the top. Now, why is this? Well, the difference here, if I make Mario, is, whoops, I need to add CS50.h because I'm now using get int. If I now compile this version of Mario and do /Mario, a do-while loop is helpful when you want to do something no matter what first and then check some condition or some Boolean expression to see if maybe, in this case, the user cooperated. It would make no sense if the user typed in, say, 0, because like there's no work to be done. It'd be really weird if they said -100, because that makes no sense logically. So with this simple construct here, I am doing the following while n is less than 1. The implication is that as soon as n equals 1 or is bigger than 1, I'm going to break out of this loop, and I've got myself a variable called n containing essentially a positive value, 1 through 2 billion or so. And I can now use this, for instance, here. Change the 4 to an n, so now my program is completely dynamic. Let me go ahead and do make Mario, /Mario again, and I'll do 4. Still works. I'll do 40. Still works. And the difference here with the do-while is if something like this involves getting user input, well, there's no question to ask. Like, the user hasn't given you anything yet, so you have to do something first, then check, and break out of the loop if the human has, for instance, cooperated in this case. All right, well, why don't we escalate to something more like this in the same game, where your underground is Mario, and this is like a 2-dimensional wall that's popping up here. It looks like a 3x3, for instance, for the sake of discussion, and it's like made of bricks, so I'll use maybe hash symbols this time. Well, it turns out that we can nest, that is, combine some of these same ideas as follows. Let me go ahead now and change back to this code, and I'm going to keep the do-while loop from before, and I'm going to ask, though, this question, what's the size of this square? I'm going to assume it's like n by n, so 3x3, 4x4, whatever, so I'm just going to ask for the size of this square of bricks. And now, how do I do this? Well, I'm going to go ahead, for instance, and print out about 4, int I gets 0, I less than n, I plus plus. Let me just keep it simple and print out something like this, just a single hash symbol that is a brick, and a new line after it. All right, let's make Mario, run Mario of 3. OK, that's close to being it. I've got a column. All right, but I need it to be wider, so the solution last time was to get rid of the new line, and then maybe put the new line here, out after the loop. All right, so let's do make Mario, /Mario, and type in 3, and, All right, so I kind of need to combine these two ideas somehow. So how might we solve this problem? I want to print like rows and columns, not row or column. How do I do this? Yeah, add another loop in the for loop, right? If you use one loop conceptually to kind of count the rows from top to bottom, and then within each row, you then sort of typewriter style, old school typewriter, do like character horizontally, I think we could do exactly what we want to achieve here. So how about this? Let me get rid of this line and get rid of this line for now, and let me just give myself another loop on the inside, and since I'm already using I, another reasonable convention here would be to say something like j. So j also gets 0, j is less than n, j plus plus, and now what's going to happen? Let me go ahead and print out just one of these things at a time. And let me save and write. Let me run this. Let me see how close we are. Make Mario is 3. OK, 3. That's clearly wrong, but I see 9 things there on the screen. So we're close. What's the one fix I need now to sort of move the old school typewriter head down to the next row when appropriate? What do you think? Yeah, I need one of these \n's, and probably, let me add some comments now to help everyone visualize what I've done. For each row, for each column, how about print a brick, just to kind of explain the logic. And so I add that because now, move to next row, I could do something like this with a \n. So here's where the comments, really my pseudocode, actually kind of illuminates the situation a bit. Let me go ahead and recompile Mario, /Mario 3. Now we're talking. It's not a perfect square just because these hash symbols are a little taller than they are wide, but that's just a font detail here. Now I've done something that's quite more akin to something like this. All right, so let me pause here and see if there are any questions. Again, the code's getting a little more complicated, but we're just building like more complicated programs like in Scratch with like familiar puzzle pieces, some variables, some loops, some conditionals. It's all the same as before. Yeah. Can you multiply strings in C? No. But ask that same question again in a few weeks when we get to Python, and the answer will be yes. Other questions? Yeah. In C, you must specify the return type, the name of the function, and the inputs or arguments to the function in that order. And if none of them are applicable, you write the word void. So same question as earlier. Let me kick that can a week or so, and we'll come back to that, and we'll see why. But for now, just take on faith that you need to do that with main, because main is a little special, similar to the when green flag is clicked. It, too, was a little special as well. Yeah. Yes, if you want to get out of a loop early, you could do this. So let me answer this question this way. An alternative to a do-while loop would be to do something like this. How about while true? So do the following forever. Let me go ahead and get an int from the user for the size of this thing. If n is greater than 0, that is a positive integer, then go ahead and use a new keyword called break. This is identical to what we just did. It's just a little longer. It's like a couple extra lines. A lot of them are blank, and so it's just an alternative. But a do-while does the same thing, but a little tighter, if that's an answer to your question. All right, so let's now introduce, finally, a sequence of problems that I've kind of been brushing under the rug, though we did see a little bit of evidence of this earlier when we tried to add 2 billion and 2 billion, and it overflowed the number of bits in an int, so to speak. Let me go ahead and code up a program called calculator again, but I'm going to go ahead now and change us to floats. So I'm going to change x to a float, and I'm going to use getFloat. And a float, again, is just a floating point value, which is a fancy way of saying a real number with a decimal point in it. And down here, I'm going to go ahead and use %f for float. And I'm going to go ahead now and do one more thing. Instead of addition, I want to do something fancier like division. So divide x by y. And I'm going to give myself another third float called z, as we did at the beginning of today, and I'm going to print out z instead of x and y explicitly. So I'm going to go ahead now and do make calculator, /calculator, and let's do something like, 2/3. 2 divided by 3 is 0.66667. So that's what you would rather expect. Let me run it again. 1/10. All right, so 0.1 and a bunch of zeros. That, too, is what you would rather expect. But now let me get a little curious. It turns out that in C, you can modify the behavior of these format codes a little bit. By default, you get like 6 or so digits. Suppose that you want to get exactly 2 digits. You can more succinctly say 0.2 before the f and after the %. This is the kind of thing that's hard to remember, but you Google it and you find that, OK, format code for floats uses 0.2 to do 2 decimal points. So let me do make calculator again. /calculator, how about 2/3, 0.67. So it handles the display of significant digits for us here. And now let me go ahead and do 1/10 and 0.10. So it's adhering to that. Well, maybe I really want a lot of precision, right? I've got a really powerful computer. Let me see 50 numbers after the decimal point. That's a lot of significant digits. Let me remake the calculator. Whoops, typo. Let me remake the calculator. Not Mario, calculator. And how about 2/3 again? Well, that's interesting. Pretty sure it's supposed to be like a 0.6 with like a line over it, right, in grade school math. All right, well, maybe that's just a bug. How about 1/10? OK, that's really getting funky. So what's going on? It seems that my program can not only not do addition very well, we eventually hit problems in the billions, we can't even do very precise numbers here. What's going on? Exactly. In a nutshell, the computer's approximating the answer using that many numbers after the decimal point. But the problem fundamentally is actually very similar to that integer overflow from before. And I'm using that now as a term of art. Integers can overflow if you're trying to use more bits than you actually have available to you. You sort of change them all to ones, and then you're out of bits, so to speak. Same thing here, but in a different context of floats. If you only have 32 bits, or heck, if we change to double and only have 64 bits, that's a lot of precision, but it's not infinite. And yet, pretty sure there's an infinite number of real numbers in the world, which is to say a computer with finite memory cannot possibly represent all possible numbers in the world because, again, there's not an infinite number of permutations of 32 or 64 bits. It might be a lot, in the billions or more, but it's still finite. And so indeed, this is the computer's closest approximation to what's actually going on there. And so this is an example of what we would actually generally call floating point imprecision. Floating point imprecision refers to the inability for computers fundamentally to represent all possible real numbers 100% precisely, at least by default, in languages like C. Thankfully, in the world of scientific computing and so forth, there are solutions to this problem that just give you more digits, but the problem fundamentally is still going to be there. So there's a reason I changed x and y to floats. Let's see what would happen if we rewound a bit, and instead of using floats for x and y, again use, say, integers. So int x and int y, and let's go far back and use getInt as well, thereby giving us integers x and y. Let's still leave z as a float, because at the end of the day, we want to be able to handle fractions or floating point values, but let's go ahead now and print out this value of z having changed x and y now to ints. Make calculator, /calculator, and let's do, say, 2 for the numerator, 3 for the denominator, and voila, it's not 0.666, and it's not even rounding oddly, it's just all zeros this time. So why is that? Well, it turns out that C, when dividing an integer by an integer, is always going to give you back an integer, an int. The problem is that floating point values don't fit in ints. Only the integral part to the left of the decimal point does. Everything at and beyond the decimal point itself gets thrown away, known as a feature in C called truncation. When dividing an integer by an integer, you get back an integer, but if you're trying to then store what's actually a floating point result in that integer, C is just going to throw away everything at and beyond the decimal point, leaving us with this case in just the 0 from what should have been 0.6666666, and so forth. So let's see one more example, in fact. Let me go back to my terminal here. Let me do /calculator again, and let's do 4/3. This time it should be 1.33333 and so forth. But let's see. 4 divided by 3, both as integers, this time gives us 1.0000, but there too. The answer should be 1.333, but the floating point part is getting truncated or thrown away, leaving us with just 1. So how do we solve this? Well, certainly, we could just use floats from the get-go as I did. But if by nature of your program you only have access to integers or maybe even longs, for which the same problem would occur, what we can actually do is called type conversion. And we can explicitly tell the computer that we actually want to treat this int as though it's a floating point value. And we can do that for both x and y. So let me go back to my code here. And I have a couple of options, in fact. I can convert y to a float by doing this. I can cast y to a float by literally writing the type float inside of parentheses right before the y. And if I really want to be explicit, I can also do the same to x. But strictly speaking, it suffices to just change one or the other, not necessarily both. Let me go ahead now and do make calculator again, /calculator, and let's try 2 divided by 3, and now we're back to an answer that's closer to correct, but indeed we're still having some rounding issues there. Let's run it one more time for 4 divided by 3. There too, we're closer to the right answer at least, but we still have that floating point imprecision, but that's going to be another problem altogether to solve. And here in a little more detail is that issue of integer overflow, which is in the context of ints. Suppose that we think back last week when we had 3 bits, and we counted from like 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. I think I asked the question, how would we count to 8? Someone proposed, well, we need a 4th bit. That's fine if you have a 4th bit, if you have access to another light bulb or transistor. If you don't, though, the next number after this is technically 1000, but if you don't have space for or hardware for that 4th bit, you might as well just be representing the number 0. So in the world of integers, if you're only using 3 bits, those 3 bits eventually overflow when you count past 7, because what should be 8 can't fit, so to speak, so it rolls back over to 0. And as arcane as this problem might seem, we humans have done this a couple of times. You might recall knowing about or reading about the Y2K problem, where a lot of people thought the world was going to end. Why? Because on January 1st of 2000, a lot of computers, presumably, were going to update their clocks from 1999 to the year 2000. The problem is, though, for decades, for efficiency, we humans were honestly in the habit of not storing years as 4 digits. Why? Because that's just a lot of space to waste, especially since like centuries don't happen that often. So a lot of computer systems, especially early on, when hardware was very expensive and memory was very tight, just stored the last 2 digits of any year. Problem, of course, on January 1st of 2000 is that 99 rolls over to 100, but if you don't have room for another digit, it's just 00. And if your code assumes a prefix of 19, well, we just went from the year 1999 back to the year 1900. Thankfully, long story short, a lot of people wrote a lot of code in a lot of old languages and mostly warded off this problem, so the world did not end. The next time the world might end, though, is on January 19th, 2038. Now, that might feel like a long time away, but so did the year 2000 at one point. Why might clocks again break in today's modern computers in 2038, might you think? Indeed. So this refers to some number of seconds. So it turns out that the way computers generally keep track of time is they count the total number of seconds since the epoch, which is defined as January 1st, 1970. Why? It was just a good year to sort of start counting at when computers really came onto the scene. Unfortunately, most computers use 32 bits to count the number of seconds since January 1st, 1970, the implication of which is we can only count up to roughly 2 billion seconds. 2 billion seconds is going to happen in 2038, at which point 31 ones are going to roll over as follows. That number 2 billion, which is the max, because if you're representing positive and negative numbers, recall that you can only count as high as positive 2 billion or negative 2 billion, looks like this. This is roughly the number 2 billion in binary. It's all ones with 1 0 way over here. If I count 1 second past that 2 billion number, give or take, that means like, all right, I add 1, I carry the 1. It's just like 9s becoming 0s in decimal. If I keep this sort of simple animation, and I keep carrying the 1, carrying the 1, carrying the 1, 1 second after 2 billion seconds, give or take, I have this number in the computer's memory. So there's still one bit that's a 1 all the way to the left. Unfortunately, that bit often represents negativity. whereby if that first bit is negative, that represents that the rest of it somehow represents a negative number. It's not negative 0. There's a fancier representation. But a very big positive number very suddenly becomes a very big negative number, and that number is roughly negative 2 billion. That means computers in 2038 on that date are going to accidentally think that it's been negative 2 billion seconds since January 1st, 1970, which is going to make computers potentially think it's 1901. So what is the solution to the 2038 problem, perhaps? Y2K was because we were using 2 digits for years. What about 2038? More bits. And thankfully, we're getting a little better at lessons learned here. And computers now are increasingly using 64 bits. And all of us will be long gone by the time we run out of that number of seconds. So it's someone else's problem many, many years from now. But that's really the fundamental solution. If you're running up against something finite, well, just kick the can further and just give yourself more bits. And frankly, because hardware is so much cheaper these days, computers are so much faster, it's not as big of a deal as it might have been decades ago. But that's indeed the solution. But this arises in very common contexts. In fact, let me go ahead and write a real quick program here called pennies. Right? You might think that just converting dollars to pennies in US currency might be simple. But let me go ahead and do this. In pennies.c, I'm going to go ahead and include CS50.h. And I'm going to include standard.io.h, int main void as my starting point. And now down here, I'm going to do this. I'm going to get a float called amount. And I'm going to ask the user for some amount of dollars, so a dollar amount. And I'm going to store that in a variable called amount. Then I'm going to simply convert that amount to pennies by doing, say, how about amount times 100. And then I'm going to go ahead and print out that the number of pennies is %i, because that's just an integer in pennies, \n, quote unquote, comma, pennies. All right, so if I didn't make any mistakes here, let me make pennies, /pennies, and suppose I have, say, 99 cents, so 0.99, that's 99 pennies. Suppose I have $1.23. That's pretty good. Suppose I have $4.20. Huh. There's that imprecision issue. And this isn't even that big of an amount. Now, not a big deal if like the cashier gives you 1 penny less than you're owed, but you can imagine this adding up. You can imagine this being worrisome for financial implications, for financial transactions, for scientific measurements and the like. My program can't even handle this. Well, there are some solutions here. And it looks like what's really happening if I print it out using the %f with a 0.50 or whatever to see more decimal points, presumably the computer is struggling to represent $4.20 precisely. It's probably storing $4.19.9999 something cents. So it's close, but it's not quite there. So I could at least solve this by rounding up, for instance. And it turns out there is a round function out there. And it turns out that it's in a library called the math library. And you would know this by looking at online documentation and the like, as we'll point you to. And if I now make pennies again and do /pennies, I can now do $4.20. And voila, now it's correct. So at least in this context, it seems like a solvable problem. But it's certainly something I need to be mindful of nonetheless. Unfortunately, even professional, full-time programmers over the years have not been particularly attentive to these kinds of details. And in a class like this, the goal is not just to teach you programming, but to really teach you what's going on underneath the hood, so to speak, so that you have a bottom-up understanding of how data is represented, how computers are manipulating it, so that you are not on the failing end of some program having some bug, and so that we as a society are not beholden to those kinds of mistakes too. And this happens, unfortunately, all of the time. This is a Boeing airplane that a few years ago needed to be rebooted after every 248 days. Why? Because this Boeing airplane software was using a 32-bit integer, counting up tenths of a second to keep track of something or other related to its electrical power. And unfortunately, after 248 days of the airplane being continuously on, which in the airline industry is apparently not uncommon to make every dollar count, keeping the planes up and running all the time, the 32-bit number would roll over and the power would shut off on the airplane as a side effect because of sort of undefined behavior in that case. The temporary solution by Boeing at the time was apparently essentially sort of operating system style, well, have you rebooted your plane? And that was indeed the fix until they rolled out an actual software patch. This stuff really matters. And the more hardware we carry around and the more we as a society use these kinds of devices, the more of these problems we're going to run into down the road. That's it for CS50. We'll see you next time.
All right, so let's talk about another thing that's kind of unique to C, which is data types and variables. And when I say unique to C, I really mean in the context of if you've been a programmer for a really long time, you've probably not worked with data types if you've used modern programming languages. Modern languages like PHP and JavaScript, which we'll also see a little later on in the course, you don't actually have to specify the data type of a variable when you use it. You just declare it and start using it. If it's an integer, it knows it's an integer. If it's a character, it knows it's a character. If it's a word, it knows it's a string, so-called. But in C, which is an older language, we need to specify the data type of every variable that we create the first time that we use that variable. So C comes with some built-in data types, and let's get familiar with some of those. And then afterwards, we'll also talk a little bit about some of the data types that we've written for you, so you can use them in CS50. The first is int. The int data type is used for variables that will store integer values, so 1, 2, 3, negative 1, 2, 3, and so on. Integers, which is something you should keep in mind for the quiz, always take up 4 bytes of memory, which is 32 bits. There are 8 bits in a byte. So this means that the range of values that an integer can store is limited by what can fit within 32 bits worth of information. Now, as it turns out, it was long ago decided that we would split up that range of 32 bits into negative integers and positive integers, each getting half of the range. So the range of values that we can represent with an integer range from negative 2 to the 31st power to 2 to the 31st power minus 1, because we also need a spot for 0. So basically, half of the possible values you can fit in an int are negative, and half are positive. And roughly here, this is about negative 2 billion to about positive 2 billion, give or take a couple hundred million. So that's what you can fit in an integer variable. Now, we also have something called an unsigned integer. Now, unsigned ints are not a separate type of variable. Rather, unsigned is what's called a qualifier. It modifies the data type of integer slightly. And in this case, what unsigned means, and you can also use unsigned other data types, the integer is not the only one. What it effectively does is doubles the positive range of values that an integer can take on at the expense of no longer allowing you to take on negative values. So if you have numbers that you know will get higher than 2 billion, but less than 4 billion, for example, which is 2 to the 32nd power, you might want to use an unsigned int if you know your value will never be negative. You'll occasionally have use for unsigned variables in CS50, which is why I mention it here. But again, the range of values that you can represent with an unsigned integer, as opposed to a regular integer, are 0 to 2 to the 32nd power minus 1, or approximately 0 to 4 billion. So you've effectively doubled the positive range that you can fit, but you've given up all of the negative values. Now, as an aside, unsigned is not the only qualifier that we might see for variable data types. There are also things called short and long and const. Const we'll see a little bit later in the course. Short and long we probably won't. But just know that there are other qualifiers. Unsigned isn't the only one, but it's the only one we're going to talk about right now. So, all right, so we've covered integers. What's next? Chars. So chars are used for variables that will store single characters. Char is short for character, and sometimes you might hear people pronounce it as car. So characters always take up 1 byte of memory, which is just 8 bits. So this means that they can only fit values in the range of negative 2 to the 7th power, or negative 128, to 2 to the 7th power minus 1, or 127. Thanks to ASCII, it was long ago decided a way to map those positive numbers from 0 to 127 to various characters that all exist on our keyboard. So as we'll see later on in the course, and you'll probably come to memorize at some point, capital A, for example, the character capital A, maps to the number 65. And the reason for that is because that's it's been assigned by the ASCII standard. Lowercase a is 97. The character 0, for the actual, when you actually type the character and not representing the number 0, is 48. You'll learn a couple of these as you go, and you'll certainly come to need them a little bit later in CS50. The next major data type is floating point numbers. So floating point numbers are also known as real numbers. They are basically numbers that have a decimal point in them. Floating point values, like integers, also can hold up to or also contain within 4 bytes of memory. Now, there's no chart here, there's no number line, because describing the range of a float isn't exactly clear or intuitive. Suffice it to say, you have 32 bits to work with. And if you have a number like pi, which has an integer part, 3, and a floating point part, or a decimal part, 0.14159, and so on, you need to be able to represent all of it, the integer part and the decimal part. So what do you think that might mean? One thing is that if the decimal part gets longer and longer, and if I have a very large integer part, I might not be able to be as precise with the decimal part. And that's really the limitation of a float. Floats have a precision problem. We only have 32 bits to work with, so we can only be so precise with our decimal part. We can't necessarily have a decimal part precise to 100 or 200 digits, because we only have 32 bits to work with. So that's a limitation of a float. Now, fortunately, there's another data type called double, which somewhat deals with this problem. Doubles, like floats, are also used to store real numbers or floating point values. The difference is that doubles are double precision. They can fit 64 bits of data, or 8 bytes. What does that mean? Well, it means we can be a lot more precise with a decimal point. Instead of having pi to 7 places, maybe with a float, we can maybe have it to 30 places. And if that's important, you might want to use a double instead of a float. Basically, if you're working on anything where having a really long decimal place and a lot of precision is important, you probably want to use a double over a float. Now, for most of your work in CS50, a float should suffice, but do know that doubles exist as a way to somewhat deal with the precision problem by giving you an extra 32 bits to work with for your numbers. Now, this is not a data type. This is a type, and it's called void. And I'm talking about it here because we've probably seen it a few times already in CS50, and you might be wondering what it's all about. So void is a type. It does exist, but it's not a data type. We can't create a variable of type void and assign a value to it. But functions, for example, can have a void return type. Basically, if you see a function that has a void return type, it means it doesn't return a value. Can you think of a common function that we've used so far in CS50 that doesn't return a value? Printf is one. Printf does not actually return anything to you. It prints something to the screen, and that's called it's basically a side effect of what printf does, but it doesn't give you a value back. You don't capture the result and store it in some variable to use it later on. It just prints something to the screen, and you're done. So we say that printf is a void function. It returns nothing. The parameter list of a function can also be void, and you've also seen that quite a bit in CS50 too. Int main void, does that ring a bell? Basically what that means is that main doesn't take any parameters. There's no arguments that get passed into main. Now later on we'll see that there is a way to pass arguments into main, but so far what we've seen is int main void. Main just doesn't take any arguments, and so we specify that by saying void. We're just being very explicit about the fact that it doesn't take any arguments. So for now, suffice it to say that void basically should just serve as a placeholder for you as thinking about it as nothing. It's not really doing anything. There's no return value here. There's no parameters here. It's void. It's a little more complex than that, but this should suffice for the better part of the course. And now, hopefully now you have a little bit more of a concept of what void is. All right, so those are the 5 types that you'll encounter that are built into C. But in CS50, we also have a library, CS50.h, which you can include, and which will provide you with 2 additional types that you'll probably be able to use on your assignments or just working generally programming. The first of these is bool. So the Boolean data type, or bool, is used for values or variables that will store a Boolean value. If you've ever heard this term before, you might know that a Boolean value is capable of only holding 2 distinct values, true and false. Now this seems pretty fundamental, right? It's kind of a surprise that this doesn't exist in C as it's built in, and in many modern languages, of course, Booleans are a standard default data type, but in C, they're actually not. But we've created it for you, so if you ever need to create a variable whose type is bool, just be sure to pound include CS50.h at the beginning of your program, and you'll be able to create variables of the bool type. If you forget to pound include CS50.h and you start using Boolean type variables, you might encounter some problems when you're compiling your program, so just be on the lookout for that, and maybe you can just fix the problems by pound including CS50.h. The other major data type that we provide for you in the CS50 library is string. So what is a string? Strings are really just words. They're collections of characters. They're words, they're sentences, they're paragraphs. It might be whole books even. Very short to very long series of characters. If you need to use strings, for example, to store a word, just be sure to pound include CS50.h at the beginning of your program so you can use a string type, and then you can create variables whose data type is string. Now, later on in the course, we'll also see that that's not the entire story either. We'll encounter things called structures, which allow you to group maybe an integer and a string into one unit. And we can use that for some purpose, which might come in handy later on in the course. And we'll also learn about defined types, which allow you to create your own data types. We don't need to worry about that for now, but just know that's something on the horizon, that there's a lot more to this whole type thing that I'm telling you just now. So now we've learned a little bit about the basic data types and the CS50 data types. Let's talk about how to work with variables and create them using these data types in our programs. If you want to create a variable, all you need to do is 2 things. First, you need to give it a type. The second thing you need to do is give it a name. Once you've done that and slapped a semicolon at the end of that line, you've created a variable. So here's 2 examples. Int letter, semicolon, int number, semicolon, char, letter, semicolon. What have I done here? I've created 2 variables. The first, the variable's name is number, and number is capable of holding integer type values because its type is int. Letter is another variable that can hold characters because its data type is char. Pretty straightforward, right? If you find yourself in a situation where you need to create multiple variables of the same type, you only need to specify the type name once. Then just list as many variables of that type as you need. So I could, for example, here in this 3rd line of code, say int height, semicolon, new line, int width, semicolon, and that work too. I still get 2 variables called height and width, each of which is an integer, but I'm allowed to, thanks to C syntax, consolidate it into a single line. Int height, comma width, semicolon. It's the same thing. I've created 2 variables, one called height, one called width, both of which are capable of holding integer type values. Similarly here, I can create 3 floating point values at once. I can maybe create a variable called square root of 2, which presumably will eventually hold the floating point representation of square root of 2, square root of 3, and pi. I could have done this on 3 separate lines, float square root 2, semicolon, float square root 3, semicolon, float pi, semicolon, and that would work too. But again, I can just consolidate this into a single line of code. Makes things a little bit shorter, not as clunky. Now, in general, it's good design to only declare a variable when you need it. And we'll talk a little bit more about that later on in the course when we discuss scope. So don't necessarily need to create all the variables at the beginning of the program, which some people might have done in the past, or certainly a very common coding practice many years ago when working with C. You might just want to create a variable right when you need it. right, so we've created variables. How do we use them? After we declare a variable, we don't need to specify the data type of that variable anymore. In fact, if you do so, you might end up with some weird consequences that we'll kind of gloss over for now, but suffice to say, weird things are going to start happening if you inadvertently redeclare variables with the same name over and over. So here I have 4 lines of code, and I have a couple of comments there just indicating what's happening on each line just to help you get situated in what's going on. So int number semicolon, we saw that previously. That's a variable declaration. Now created a variable called number that's capable of holding integer type values. So I declared it. The next line, I'm assigning a value to number. Number equals 17. What's happening there? I'm putting the number 17 inside of that variable. So if I ever then print out what the contents of number are later on, it'll tell me it's 17. So I've declared a variable, and then I've assigned it. We can repeat the process again with letter, char letter, semicolon, that's a declaration. Letter equals capital H, that's an assignment. Pretty straightforward too. Now, this process might seem kind of silly. Why are we doing this in 2 lines of code? Is there a better way to do it? In fact, there is. Sometimes you might see this called initialization. It's when you declare a variable and assign it a value at the same time. This is actually a pretty common thing to do when you create a variable. You usually want to have some basic value, whether it's even if it's 0 or something, you give it a value. So you can initialize a variable. Int number equals 17 is the same as the first 2 lines of code up above. Char letter equals H is the same as the 3rd and 4th lines of code above. The most important takeaway here when we're declaring and assigning variables is after we've declared it, notice I'm not using the data type again. I'm not saying int number equals 17 on the second line of code, for example. I'm just saying number equals 17. Again, redeclaring a variable after you've already declared it can lead to some weird consequences. Just be careful of that. I'm Doug Lloyd, and this is CS50. All right, so let's talk about operators in C. So we've already seen one, in fact, equals the assignment operator. It allows us to put a value. All right, so let's talk about operators in C. So we've already seen 1, in fact, equals the assignment operator. It allows us to put a value into a variable. That's the assignment operator, single equal sign. In order to manipulate and work with values and variables in C, we have a number of operators at our disposal that we can use. Let's take a look at some of the common ones, starting with arithmetic operators. As you might expect, we can do pretty basic math operations in C. We can add, subtract, multiply, and divide numbers using plus, minus, star, and and slash, respectively. Here's a couple of lines of code in which we do that. So we have int x equals y plus 1. So let's assume that somewhere up above this line of code we had said int y equals 10. What's the value of x after I execute this first line of code? Did you say 11? You'd be right. Why is that? Well, y was 10, so I'm saying int x equals 10 plus 1. 10 plus 1 is 11, so the value 11 gets stored in the variable x. Not too bad, right? How about this next line of code? X equals x times 5. Well, before we executed this line of code, x was 11. So what is the value of x after this line of code? Take a second. So x equals x times 5. X was 11, so x equals 11 times 5, or 55. So if you said 55, you'd be right. Now, it's maybe a little confusing, but the way that assignment works in C is the value on the right gets assigned to the value on the left. So first we evaluate x times 5, so 11 times 5 is 55, and then we store that value in x. The 11 that was there before is now overwritten, so x's value is now 55. Hopefully that's fairly straightforward. There's another operator that you've probably not necessarily heard called this, but you've certainly worked with in the past if you remember your days of long division way back in grade school. It's called the modulus operator. What modulus does is it gives you the remainder when you divide two numbers together. So if I say 13 divided by 4, what's the remainder? And that value would be calculated by the modulus operator. So I have a line of code here, int m equals 13 mod 4, and I say here in a comment that m's value is now 1. Why do I say that? Well, do the long division on your head if you bear with me for a second. So I have 4, and then divide by 13. 4 goes into 13 3 times, with a remainder of 1. So that's basically all the modulus operator does is it tells you when you divide, you get the remainder. You might think that that's actually not a terribly useful thing, but you'd be surprised actually by how frequently that modulus operator can come in handy. There's a couple of problems we'll do in CS50 that deal with it. It's also good for doing things like random numbers. So for example, if you've ever heard of a random number generator, that's going to give you a number from 0 to some huge number, but maybe only really a number from 0 to 20. If you use the modulus operator on that giant number that gets generated by the random number generator, you're going to take whatever huge value it is, divide it by 20, and get the remainder. The remainder can only be a value from 0 to 19. So you use modulus operator to take this huge number and whittle it down to something a little more meaningful. I'm pretty sure you'll be able to use both of those at some point in the future in CS50. So C also gives us a way to apply an arithmetic operator to a single variable in a little more shorthand way. So in the previous slide, we saw x equals x times 5. That worked. X times 5 then gets stored back in x. There's a shorter way to do it, though, and it's the syntax x times equals 5. It's the same exact thing as saying x equals x times 5. It's just a slightly shorter way to do it. And when you see some distribution code or you see some sample code that does things like this, just be familiar with what the syntax means. You certainly don't have to use it, but if you do, it might make your code look a little slicker. And note you can also use any of the different operators we've already seen before instead of times. So you can say x plus equals 5, minus equals 5, times, divide, and mod. All of those work. There's also something that's so common in C that we've decided to refine that even further. Incrementing a variable by 1 or decrementing a variable by 1 is such a common thing, especially when we talk about loops a little later on, that we've decided that instead of saying something like x plus equals 1 or x equals x plus 1, we've even shorthanded that to x plus plus. So x equals x plus 1, x plus equals 1, and x plus plus all do the same thing. They all increment x by 1. But that incrementing and decrementing by 1 is so common that we have plus plus and minus minus that allow us to shorthand that even further. So let's switch gears for a second and talk about Boolean expressions, all of which are also kind of fall into the overall category of operators, but Boolean expressions, unlike arithmetic operators, are used for comparing values. So again, all Boolean expressions in C evaluate to one of two possible values. Are called true or false. That's the only two values a Boolean variable can take on. We can use the result of a Boolean expression in a lot of ways in programming. In fact, we'll be doing this quite a lot. For example, we might decide, well, if some condition is true, maybe I'll take this branch down my code, a conditional, so to speak, and we'll learn about those soon too. Or maybe as long as this is true, I want to keep doing this over and over and over, a loop. In both cases, note we're using a Boolean expression, a true or false, to decide whether or not to take a particular path. Sometimes when we're working with Boolean expressions, we will use variables of type bool. You might have declared bool type variable, and you'll use it in your Boolean expression, but you don't always have to. As it turns out, in C, every non-zero value is the same as saying true. If you would declare a Boolean of a variable type Boolean and assign the value true, that's the same as declaring an integer and assigning the value 1, 2, 3, or really any value whatsoever other than 0. Because in C, every non-zero value is true. 0, on the other hand, is false. This might come in handy later on to know, but just something to keep in mind. We don't always have to use Boolean type variables when we are working with Boolean expressions. There are two main types of Boolean expressions that we'll work with, logical operators and relational operators. The language there is not terribly important, it's really just how I'm grouping them. And you'll certainly, I think, quickly realize what a relational operator is based on what they are when we talk about them in a second. But don't worry about necessarily memorizing the term logical operator or relational operator. I'm just using it to group them in a logical way. So let's take a look at the three logical operators that we'll see quite a bit in programming in CS50 and programming more generally. Logical AND is true if and only if both operands are true, otherwise false. What does that mean? So let's say that I am at a point in my code where I have two variables, x and y, and I want to decide whether to do something in my code based on if x is true and y is true. I only want to do it if both of them are true, otherwise I don't want to go down that path because it's not going to help me. What I can say is if x ampersand ampersand y. That will be a logical Boolean expression comparing x and y and taking a certain path based on what their values are. So if x is true and y is true based on this truth table here, only then will we go down that path if x ampersand ampersand y. It's only true. The and is only true if x is true and y is true. If either one of them is false, as we see in the truth table, then both x and y are not true, and so x ampersand ampersand y is false. Logical OR is true if and only if at least one operand is true, otherwise false. So logical AND requires both x and y to be true. Logical OR requires x to be true, or y to be true, or both x and y to be true. So again, we kind of find ourselves in a situation where we're going through our code and we reach a fork in the road, and we want to go down a particular path if x is true or if y is true. But not necessarily if both are true, but possibly if both are true. So if x is true and y is true, we'll go down the path. X is true, one of them is true, right? If x is true and y is true. If x is true and y is false, one of them is still true, so x or y is still true. If x is false and y is true, no, one of them is still true, right? Y is true in this case, so it's true that x or y is true. Only if x is false and y is false do we not go down that path, because neither x nor y is true. Now, you're looking at the screen right now and wondering what that symbol is for logical OR. It's called the vertical bar. And if you look at your keyboard for a minute, as I'm doing now, it's usually just above the Enter key on most keyboards, on the same key as the backslash. It's also usually right next to the square brackets. So it might be a key that you haven't typed very much in the past, but if you're ever doing logical comparisons, as we'll be doing a lot in the course, it's going to be useful to find that key and use it. So it's usually on the same key as backslash, just above Enter. The final logical operator is not, and not's pretty straightforward. It inverts the value of its operand. If x is true, then not x is false. If x is false, then not x is true. Sometimes you'll hear this symbol pronounced as bang or exclamation or not. It's pretty much the same thing. But in case you hear that spoken and you're not sure what that means, it's just the exclamation point, but sometimes it's called a couple different things. All right, so that takes care of logical operators. So let's talk about relational operators. Again, if you're familiar with this arithmetic back in grade school, you're probably familiar with how these work already. These behave exactly as you'd expect. So less than is true in this example if x is less than y. So if x is 4 and y is 6, x is less than y. That's true. Less than or equal to works pretty similarly. If x is 4 and y is 4, then x is less than or equal to y. Greater than, x is greater than y, and greater than or equal to, x is greater than or equal to y. If it's true, then you'll pass that expression and you'll go down that path in the road. If you have an if x is greater than y and x in fact is greater than y, you'll do whatever is subject to that condition. Notice that we don't have a single character for less than or equal to, as you might be familiar with from math textbooks. So we have the less than symbol followed by an equal sign. That's how we represent less than or equal to. And similarly, we do that for greater than or equal to. The final two relational operators that are important are testing for equality and inequality. So if x equals y is true if x and y's value is the same. If x is 10 and y is 10, then x equals y is true. If x is 10 and y is 11, x equals y is not true. We can also test for inequality using exclamation point or bang or not again. If x is not equal to y, then if that's the test we're using here, we'll be good to go. So if x is not equal to y, we'll go down that path. Be really careful here. It's a really common mistake, and one I certainly made quite a lot when I was getting started, to accidentally mistake the assignment operator, single equals, for the equality comparison operator, double equals. It'll lead to some weird behavior in your code, and usually the compiler will warn you about it when you try and compile your code, but sometimes you might be able to sneak it by. It's not necessarily a good thing that you sneak it by, though. Just so if you are doing an equality test, if you're checking whether two different variables have the same value inside of them, make sure to use equals equals and not single equals, and that way your program will have the behavior you intend. I'm Doug Lloyd, and this is CS50. All right, so now let's talk about something really useful in programming, conditional statements. So conditional expressions allow your programs to make decisions and take different forks in the road, something I alluded to a little earlier, depending on the values of variables or based on what the user inputs at the program or at the command line, or if you have prompts or something like that. C has a couple of different ways to express conditional expressions, which we also sometimes will call a conditional branch in your program. And some of these are going to look pretty familiar to you from scratch, so we'll even pull them up side by side just so you can make an analogy in your head. So if is a pretty simple conditional. If you recall from scratch on the right here, you could fill in that hexagon with a Boolean expression, if mouse down, or if x is less than 10, or something like that. And then if x was less than 10, or if the mouse was in fact down, all of the code inside of the puzzle piece would execute, all the things that fit inside that C shape. Similarly, we have if on the left there, if Boolean expression, which I'm just using as a substitute for one of the Boolean expressions we previously discussed, open curly brace, close curly brace. So think of open curly brace and close curly brace as sort of analogous to the sandwich effect of the if block on the right from scratch. If the Boolean expression in the if statement is true, then all the lines of code between the curly braces will execute in order from top to bottom. If the Boolean expression is false, we'll skip over everything in between the curly braces because we only want to go down that fork in the road if the Boolean expression is true. We can take this one step further with if else. So this scratch block is pretty similar to the one we saw just a second ago, except it takes two different paths based on what happened. So if the mouse was down or if x was less than 10, we'll do everything that's in between that first fork, that first C. Otherwise, if the mouse is up or x is not less than 10, we will do everything in the second set. And that's analogous to what you see here for C. If Boolean expression, do the stuff between the first set of curly braces, else do the stuff between the second set of curly braces. So if the Boolean expression is true, we'll do whatever's between the first set. If the Boolean expression is false, that would trigger the else, and we would do whatever is in the second set of curly braces. Again, top to bottom, all the lines in between the braces. In C, it's possible to create an if, else chain. In fact, you can have if, else if, else if, else if, and so on and so on and so on. In Scratch, this required nesting the blocks. You had an if, else, and then you had to put another one inside of the else, and so on and so on. It got kind of nested and complicated. But C, we don't have to do that. We can actually just have it be a chain like this. Again, as you might expect, all of these branches are mutually exclusive. You can only ever go down one of the branch. If this is true, otherwise if this is true, otherwise if this is true, otherwise do this. So all four of the branches in this example are mutually exclusive. It's an if, else chain. It is possible, though, and sometimes very useful, to create a chain of not mutually exclusive branches. In this example, only the third and fourth branches are mutually exclusive. It could be that you could satisfy the first condition, and you could satisfy the second condition, and you could satisfy the third condition, in which case you would go down the first branch, then you would go down the second branch, then you would go down the third branch. Or perhaps you satisfy the first condition and the second condition, but you don't satisfy the third condition. In this case, you go down the first branch and the second branch, and then the fourth branch. The reason for this is that the else will only bind to the nearest if. So even though there's an else here, that doesn't necessarily create a mutually exclusive chain of everything. It's only that the expression there with Boolean expression 3, that's the mutually exclusive with the else. So it is possible, and sometimes quite useful, as I said, to create a chain of not mutually exclusive branches. Let's take a look at a different kind of conditional, which you have not seen before in Scratch. There's something called the switch statement. The switch statement is kind of neat because it's a conditional statement that allows you to specify distinct cases instead of relying on Boolean expressions to make decisions for you. So for example, let's say that I have this program and I'm asking the user to provide input to me. So I say int x equals getInt, and if you're not familiar yet, getInt as a function is also included in the CS50 library. So if you pound include CS50.h, you'll have access to getInt and all its cousins, getFloat, getString, and so on. Basically one get function for every data type that we've already discussed. So int x equals getInt. Basically what's happening is I'm at the terminal, I'm asking the user to type in a number. And here I'm switching what I'm doing depending on what the user typed at the prompt. So if they typed 1, I print out 1, and then I break. If they print 2, if they typed 2, I print out 2, and then I break. It's important to break between each case because otherwise you will fall through. So if I didn't have any breaks there and the user typed 1, what would happen is it would print 1, 2, 3, sorry. That's kind of strange behavior, right? You might think so, but there are actually some cases where this could be a pretty useful thing. So here's another example of a switch statement where I omit the breaks, but I do it on purpose. So what happens here? Think for a second. Maybe want to pause the video. What happens here if the user types 4? So I've asked the user for input, and they provide the value 4. What gets printed when I do that? On the previous slide, there were breaks between all the cases, and so it would just print 4 and then stop. But in this case, it won't. What will happen is you will fall through each case. So in this case, I organize my cases in such a way that if the user types 4, I will print 4, 3, 2, 1, blast off. And if they typed 5, I would start at 5 and do the same thing. If they typed 1, I would just do 1, blast off. So in this case, I'm using a switch kind of cleverly, so that I do intend to fall through all cases. But generally, you're probably going to want to break between all of them unless you have a situation like this one, where you're kind of leveraging the fact that you'll fall through the cases without a break. that's the second of the major types of conditional statements, the last of which is question mark colon. So I have two snippets of C code here, one on the left and one on the right. The one on the left should probably be pretty familiar to you. I have int x, and I probably should have, ask the user for it. It should probably be int x equals get int or something like that. And then I'm making a decision. If some Boolean expression is true, assign x the value 5. Otherwise, assign x the value 6. That on the left you're probably pretty familiar from my discussion of if else just a moment ago. Would you be surprised to know that the line on the right does the exact same thing? So this is called question mark colon, or sometimes called the ternary operator. And it's pretty cool. It's usually used as a cute trick. But what it allows you to do is to simulate an if-else with really small, really trivially short conditional branches. You generally wouldn't use question mark colon if you had 6 lines of code between each set of curly braces. But if you're just making a quick decision, if you're going to do one thing or the other, and it's very simple, this might be an example of how you do it with question mark colon, the ternary operator. So int x equals expression, question mark. The thing after the question mark is what x's value will be if the expression is true. The thing after the colon is what x's value would be if the expression was false. So I'm asking myself, is the expression true? If it is, assign x the value 5. If it's not, assign x the value 6. Again, like I said, this is usually just a cute trick, and sometimes if you become really comfortable with it, you'll do this because it looks kind of cool in your programs. Generally, I'm presenting it to you now so that you're familiar with it if you see it. But certainly you don't have to write it in any of your code, but it is something to be familiar with because you'll definitely encounter snippets of code here and there where this question mark colon syntax, aka the ternary operator, is used. So a quick summary on what conditionals are and what the options are available to you in C. You have if and if else and if else if, etc. You can use Boolean expressions for those to make decisions. With switch statements, you use discrete cases to make decisions. You explicitly say, if it's 1 or if it's 2 or if it's 3, I'll do this thing or this thing or this thing. And question mark colon can be used to replace very simple if-else branches or if-else chains to make your code look a little fancy. I'm Doug Lloyd, and this is CS50. Two different paths based on what happened. So if the mouse was down, and if else, and then you had to put another one inside of the else, and so on and so on. It got kind of break. If they print 2, if they typed 2, I print out 2, and then I break. It's important to break between each case because otherwise you will fall through. So if I didn't have any breaks there, and the user typed 1, what would happen is it would print 1, 2, 3, sorry. That's kind of strange behavior, right? You might think so, but there are actually some cases where this could be a pretty useful thing. So here's another example of a switch statement where I omit the breaks, but I do it on purpose. So what happens here? Think for a second. Maybe want to pause the video. What happens here if the user types 4? So I've asked the user for input, and they provide the value 4. What gets printed when I do that? On the previous slide, there were breaks between all the cases, and so it would just print 4 and then stop. But in this case, it won't. What will happen is you will fall through each case. So in this case, I organize my cases in such a way that if the user types 4, I will print 4, 3, 2, 1, blast off. And if they typed 5, I would start at 5 and do the same thing. If they typed 1, I would just do 1, blast off. So in this case, I'm using a switch kind of cleverly, so that I do intend to fall through all the cases. But generally, you probably don't want to break between all of them unless you have a situation like this one, where you're kind of leveraging the fact that you'll fall through the cases without a break. So that's the second of the major types of conditional statements, the last of which is question mark colon. So I have two snippets of C code here, one on the left and one on the right. The one on the left should probably be pretty familiar to you. I have int x, and I probably should have, ask the user for it. It should probably be int x equals get int or something like that. And then making a decision. If some all right, so let's talk about loops. So loops are kind of cool because they allow your program to execute lines of code over and over and over repeatedly without having to copy and paste or otherwise repeat them. There are three major kinds of loops in C, and you'll probably have occasion to use each one as you progress to CS50. Some of these loops are pretty familiar to you from scratch, so again, as we do with conditionals, we'll put them side by side if there is an analogy that we can draw. First is forever from scratch, which compares to while true. This is what we call an infinite loop. The lines of code between the curly braces, much like the puzzle pieces that fit inside the C of the forever block, will execute repeatedly from top to bottom over and over and over forever. After all, if you recall from our discussion of Boolean expressions, true is always true. So if we're doing something so long as true is true, it seems a little silly, true is always true, so it'll always run. It'll run forever and ever and ever until we find a way to break out of it with a break statement, which again we saw a little while ago when we were talking about switch, or otherwise just kill our program, which incidentally, if you ever find yourself in a situation with an infinite loop and you don't know how to stop your program from running, just hit Control and C, and that'll kill your program for you. But this again is called an infinite loop. It is a loop that will run forever. Now, while loops are not always infinite, we can also replace the Boolean expression with something a little more useful than just true. So here's another example. While, and then some Boolean expression, and then curly braces. That's pretty much analogous to repeat until from scratch, although in a second I'll explain the difference. So in C, if the Boolean expression inside of the while loop evaluates to true, the lines of code between the curly braces will execute repeatedly over and over and over until Boolean expression evaluates to false. So for example, you might have some sort of counter. So say you at the beginning of this loop you say int x equals 0. While x is less than 100, do a couple things inside that curly braces, and at the end of your loop you say x plus plus. You're incrementing x, so eventually x will get to 100, and you will stop because the condition x is less than 100 will no longer be true as soon as x is equal to 100, because 100 is not less than 100. Now, somewhat confusingly, the behavior of the scratch block is reversed, so be really careful if this is your first foray into using loops. Basically, the repeat until block in scratch will repeat something over and over and over until the expression, the Boolean expression in the hexagon, is true. So we'll keep doing it until it is true. Meanwhile, the while loop will continue to do it until it is false. So they're quite similar, but there's that little distinction just to be careful of, especially as you make your first foray from transitioning to scratch into C. The next kind of loop is actually pretty similar. It's called a do-while loop. This loop will execute all the lines of code between the curly braces once, and then it will check the Boolean expression. If the Boolean expression evaluates to true, it'll go back and it'll repeat that process over and over and over until the Boolean expression evaluates to false. So this loop, unlike a while loop, is guaranteed to run at least one time. It's pretty useful. Lastly, we have a for loop. For loops are kind of syntactically unattractive, and there's a lot going on here, so bear with me as we try and break these pieces apart. Generally, the use case of a for loop is you want to repeat something a specific number of times. In this example here, I have the repeat block from scratch, which is analogous to the for loop in C, repeating something 10 times. And the for loop on the left there, which is, would do the same thing. This would go 10 times. Counting from 0, we increment I each pass through the loop, and we keep doing that until I is less than 10. So what happens? There's a whole lot of code there. Let's break it down into what is happening step by step as we dig through a for loop. The first thing that happens is the counter variable is set. Everything to the left of that first semicolon inside the parentheses is executed. In this case, we are saying int I equals 0, declaring a new variable called I. That variable is of type integer, and we're saying the value inside that variable is going to be 0. The second thing we do is we then immediately evaluate the Boolean expression. The Boolean expression is in the middle of the two semicolons. I is less than 10. That's true here, right? We just said I is equal to 0, and so 0 is less than 10, and so that condition is true, and we'll now proceed to execute the body of the loop. If it was false, if, for example, I said, instead of I equals 0 there, I had said I equals 15, int I equals 15, well, 15 is not less than 10, so we would never enter the body of the loop, because the condition of the Boolean expression there would evaluate to be false. After we go through from top to bottom, we encounter that closing curly brace. A third thing happens. The counter variable is incremented, or rather, the lines of code or the statements after the second semicolon inside of the for loop's parentheses is executed. So we start out by saying int I equals 0. Then we check whether or not the Boolean expression is true. 0 is less than 10, so it's true. So we're going to proceed into the body of the loop. Things will happen inside the loop, and we encounter that closing curly brace. The next thing we do is we say I plus plus. So I was 0, now I is 1. Then we again check the value of the Boolean expression in the middle. 1 is less than 10. So we'll go through this process again and again. We'll get to the closing curly brace again. We'll increment I from 1 to 2, then from 2 to 3, and so on and so on and so on until eventually I's value becomes 10. Is 10 less than 10? No. Counting from 0, we've gone through 10 iterations of the loop. We've repeated 10 times, just as we did in the scratch block. And so that's basically the process for a for loop. Now, taking away the actual code and putting it in some sample, just some basic general statements, here's what happens. All of the statements in start are executed first. You might have more than one. Then the Boolean expression is checked. If the expression evaluates to true, execute the body of the loop one time. If the expression evaluates to false, we're done. We don't execute the body. Body loop at all. After we've executed the body of the loop one time, we then do what is in the increment part there, which is usually something like I++ or something like that modifies a counter variable. Then after we increment, we check the expression again and repeat those steps over and over and over until the expression is no longer true. So what are the use cases for a loop? You use a while loop when you want a loop to repeat an unknown number of times, but it possibly might not run at all. A really common example of a while loop being used is to run the control flow for a game. You might not know how long the user is going to be playing, but you want to keep doing the same thing, flow for a game. You might not know how long the user is going to run at all. A really common example of a while loop being used is to run the control flow for a game. You might not know how long the user is going to be playing, but you want to keep doing the same thing, updating the positions of various sprites on the board. You want to keep things moving at all times, but you don't know when the user is going to stop playing or when they're going to run out of lives. So a while loop is really good for something like that. That's a good use case. For do while loop, it's pretty similar. You want a loop to repeat an unknown number of times, but at least once. You might use this for a game too, but a really common use case is prompting the user for input. Generally, you might say something like, give me a positive integer. And you might put that inside of a do while loop. So always ask them at least once for a positive integer. If they give you a positive integer, you might break out of the loop. You might be done. The Boolean expression in the do while might be false, and you won't ask them again. If they give you a negative number, though, or they type some word or something that's not really useful to you, you might use a do while loop to go back and do it again and again and again. You definitely want to ask them to give you a number once, but you don't know how many times after that they might be tests. And so a do while loop is a great use case for prompting the user for input. And a for loop's use case typically is when you want to repeat a loop a discrete number of times, though you might not know the number of times at the moment the program is compiled. So for example, maybe you have a program where you prompt the user for a number, say, and they enter 100. And maybe your for loop will then in that case run 100 times. Or maybe they enter 1,000, and your program would then run the loop 1,000 times. It's a specific number of times, but you don't necessarily know what that number is the moment the program is compiled. It's not like a while loop where it could be infinite. It's rather a number that you just don't know. Now, even though I've outlined all these use cases, you should know that in pretty much every circumstance, you can interchange all three of these loops. You can use a for loop where you otherwise use a while loop. You can use a for loop where you use a do while loop, and so on. It can be a little tricky sometimes, so generally it's good practice to adhere to a typical use case. Use a do while loop if you want to do something once at least. Use a for loop if you want to do something a specific number of times. After all, that's why there are 3 different kinds of loops, so that they can be used in the right context. But you can interchange them if you want. If you feel comfortable with while loops and you always want to use while loops, it is something that you can do, although it might be a little syntactically tricky, where a for loop would be a lot more straightforward. My name is Doug Lloyd, and this is CS50. Okay, so let's talk about how to use the Linux command line. Now, the CS50 IDE, or in fact even the CS50 appliance, if you're familiar with that or you're taking an older version of CS50, is a cloud-based machine which runs Ubuntu, which is one of the many flavors of the Linux operating system. Linux operating system is favored by programmers because it's just cooler, right? Many modern Linux distributions have graphical user interfaces, which we also call GUIs, GUI, to allow easy mouse-based navigation, which you're probably familiar with if you're a Windows or Mac user, moving around your mouse, double-clicking on icons, and so on. Still, though, as a programmer, and even though the IDE contains the ability to do some graphical user stuff, clicking and dragging and all that, you'll still be using your terminal window pretty frequently, and you can do many of the same tasks that you can do with a mouse with keyboard commands. And we're going to talk a little bit about what some of those commands are right now. Now, these commands can be used on any Unix-based operating system, which includes Linux, but also includes Mac OS. If you open up terminal on your Mac, you can do this. You can use these exact commands. Windows also has command prompt, but some commands are slightly different, so it doesn't actually work because Windows is not a Unix-based system. So let's take a look at some of these Linux commands. The first one that you probably use quite a lot is ls. That's a lowercase l followed by a lowercase s, which is short for list. Now what the list command does is it gives you a readout of all the files and folders in your current directory, so you can see everything you can get to from where you currently are. So I've opened up here the CS50 IDE, and I'm going to zoom in a second to give you a closer look, but here's a broad picture of what the IDE looks like. On the left, you can see we have a file tree, which you're probably familiar with, double-clicking and files and folders and all that stuff, so that's still there in the CS50 appliance. At the center and the top is where you're going to be writing your code once you click on a file, and at the bottom we have a terminal window, which is where we can execute these terminal commands. I'm going to zoom in and head over here just to show you that, in fact, I do have, I can click on these files and folders. So clearly where I currently am, I have two folders called pset0 and pset1, and three files, one called hello, one called hello.c, and one called hello.txt. So let's move down to the terminal window and get a closer look. So we just talked again about the fact that we have three files and two folders in the current directory. If I type ls, which again is the command to list the contents of the current directory, and then I hit enter, look what I see. Hello, hello.c, hello.txt, pset0, and pset1. Pset0 and pset1 are colored blue to indicate to you that those are directories that we could navigate into, and we'll learn a little bit about how to navigate into directories in a minute. And every other thing is colored black if it's a text file or source code file, and green if it's an executable file. So clearly that means that I could run a program called hello. That's what the green one there means. But basically typing the ls command has allowed me to look at everything that exists in my current directory, which matches what we see here in the graphical display the same. The next command you probably use quite a bit is cd. Lowercase c, lowercase d, which is short for change directory. This allows us to do what I was just talking about a second ago, which is to navigate between directories at the command line as opposed to double-clicking on folders. So if we type cd and then the name of a directory, we can get into that directory. As an aside, know that the name of the current directory is always dot, and the name of the directory one level above where we are now, that is the name of the folder in which our folder is dot dot, or in which our folder is dot dot. And if you're ever curious about the name of your directory, you can type pwd, which stands for present working directory. We'll take a look at all of these now by heading back to the CS50 IDE. So I'm back in my workspace now. I'll zoom in again on the terminal, so we can take a look at moving around within the IDE. So I'm going to list the contents of my directory again, just to reground us in where we are. So if I type ls, which is for list again, I see that I can get to pset0 and pset1. Those are the directories I can get to from here. I know that because the IDE gives me a clue by coloring them blue. Let's say that I want to get into my pset1 directory, because I'm working on problem set 1. I can type cd, again short for change directory, space pset1. And if I hit enter, notice what happens. It doesn't look like a lot has happened, but if you look at the prompt, it now tells me that I'm in tilde/workspace/pset1. I've navigated into the pset1 folder that was within my workspace. And if I type ls, I see some different stuff here, right? This isn't the same list that I saw before. I've navigated into pset1, and so now when I type ls, I'm getting the context of what can I see from within the pset1 folder. Now I'm going to type Control L, which just clears the screen. And I'm going to list the contents of the directory again just so you can see. I just wanted to do that to clear out some of the stuff that you saw down below and prevent us from going too far down out of range. Now I said earlier that if I want to navigate to the current directory, I can type cd space dot and hit enter. It doesn't do anything, right? I'm changing directories to the current directory. You're not always going to find a need for single dot, but you will occasionally. Let's say that I want to move up one level. I want to get back to my workspace directory. I can't type cd workspace. There's no such file or directory. And the reason for that, if I type ls one more time, is that there's no directory called workspace inside of my pset1 directory. I'm going to clear my screen again with Control L. Remember what I said earlier that we can navigate back with dot dot, that's the name of the parent directory? So if I type cd space dot dot and then hit enter, now look at what happened. My command prompt tells me that I'm back in my tilde/workspace directory. I moved up one level thanks to dot dot. Now, let's say that I'm using an operating system that is Linux-based, but doesn't necessarily tell me where I am. This one happens to tell us that I'm in tilde/workspace right now, right at the prompt. But I could be completely lost in a mess of folders, and I have no idea where I am and no idea where I want to get back to. There's two things I can do. First of all, I can figure out where I am by typing pwd. That's my present working directory. And if I hit enter, it tells me exactly where I am. Now, /home/ubuntu is the long way of saying tilde, which is your home directory. But it tells me that I'm in home, Ubuntu, workspace, or tilde/workspace. I'm going to navigate to my pset1 directory again. And I'm going to list the contents. I see that I have another directory there called extras. So I'm going to cd into extras, and I'm going to clear my screen. So now I'm pretty far in, right? Like I have, what if I want to get back to workspace immediately? There's a couple things I can do. I can type cd dot dot slash dot dot to move up one level and then another level, but that's kind of annoying. So if I ever want to get back to just my home directory, tilde, I can type cd with nothing after it. Cd enter, and now I'm in tilde. And if I want to get to workspace, I can just type cd workspace. And that's how you work changing directories within the CS50 IDE or any Linux operating system at the command line. All right, the next one that might come in handy is mkdir, which is short for make a directory. If I need to create a new folder. If you're familiar with a GUI operating system, you might right-click, and then when the context menu pops up, choose new folder. That's probably how you've done it before, but we can also create directories at the command line. So back in the IDE, I'll zoom in on the terminal and list the contents of my directory again just to get us back, just to give us a frame of reference. Let's say that now I finished working on problem set 0 and problem set 1, so I want to create a new directory to work on for problem set 2. How do I do that? Well, again, I could right-click on the left side there and choose new folder and create a pset2 directory. That would work too. But I can also do it at the command line pretty quickly by typing mkdir space, I typed an n space, pset2. If I hit enter and I list the contents of my directory again, I see that, look, now I have a pset2 folder, and I can navigate into that using cd and do all the work I need to do for pset2. Incidentally, I'll just pop over here really quickly to the file tree, and you can see that also in the graphical file explorer, we can see that the pset2 directory has also been created there, and I can navigate to it using the GUI as well. The next command that's probably going to come in handy is cp, which is short for copy. Copy, unlike all the other commands we've seen before, takes two arguments: a source, the name of the file that you want to copy, and a destination, where you want to copy the file to. It's pretty easy to copy a file, so let's do that. So we're back in the IDE, and I'm going to list the contents of my current directory with ls. Now let's say that I want to make a copy of hello.txt. Again, from the file tree on the left, the graphical interface, I could right-click on hello.txt, make a copy, paste the copy, but I can do it pretty quickly with the command line too. Let's say I want to copy hello.txt to hi.txt. I can cp space hello.txt. That's my source file, so that's why I'm going to choose that one first, and then I need to name the destination file hi.txt. I hit enter, and if I list the contents of my directory again, there's hi.txt. I made a copy of it. And in fact, if I went into hi.txt, I could see that it would be an exact duplicate of everything that existed in my hello.txt file. So that's how you copy a file. But what if you want to copy an entire directory? So for a second, let's take a look at what's in my pset0 directory. If I cd pset0 and list the contents, I have a directory called sample and a scratch file, scratch.sp2. So that's good to know. So let's clear the screen, and I'm going to go back to my workspace directory for a second. Let's say that now I want to make a copy of my pset0 directory. I can't just say cp pset0 pset3, for instance. You get this weird message, omitting directory pset0. Why do you get that message? Well, it turns out that when you have a directory that has other stuff inside of it, the cp command doesn't really necessarily know what to do with it. We need to explicitly tell Linux, the terminal, I want you to copy the pset0 directory and copy every folder that exists inside of it, and every file that exists inside of it. In other words, I need you to recursively dive down into pset0 and make a copy of everything in there. If I want to do that, what I can do is cp-r for recursive, pset0, pset3, hit enter. Now, if I list the contents of my directory, I see there's the pset3 directory that I can work with. And if I cd into pset3 now, and then list the contents, look, there's sample and scratch.sp2 again. So that's pretty cool. So that's how you can copy an entire directory and not just a single file. So if you want to copy a directory, just remember to use the -r flag when you're working with the cp command. All right, so I've copied a file, but I've done it by mistake, and now I want to get rid of it. How do I do that? Again, if you're familiar with a GUI interface, you can right-click and just choose delete, and it'll send it to the trash or the recycle bin. But the command line, you can just type rm for remove, and the name of the file we want to get rid of. Now, rm is very careful. Make sure that it does a lot of double checking to make sure that you actually want to delete the file. It doesn't want to make any mistakes because there's no recycle bin here. Once we delete a file, it's gone. There's really no way to recover it. So we need to be pretty careful, and so rm is going to be really careful for us. So let's go back to the IDE and get rid of that hi.txt file that I created a minute ago with copy. So we're in the IDE, and I list the contents of my directory again just to give us some context, and we can see that there's hi.txt, which I created a little while ago. Now I want to get rid of it. How do I do it? Again, just rm. So I can type rm hi.txt, hit enter. And there's rm being really careful for us and making sure we actually want to delete this file. Do you really want to remove regular empty file hi.txt? That's just like an operating system like Windows or Mac. You might be familiar with popping up that box that says, are you really sure you want to do this? I'm pretty sure I want to do this. So I'm going to type yes, or I can also just type y and hit enter. And if I list the contents of my directory again, hi.txt is on. Not bad, right? Let's press Control L just to get rid of all this stuff and get us back to the top of the screen. Now, there is a way to short circuit rm so that it doesn't ask us that question. We really know we want to get rid of that file, and we don't even want to be asked the question. How do we do that? Well, we can specify an extra flag, just like we did with CP, where we could add the -r flag to recursively copy into a directory. There's another flag for rm, which is -f, which is to force rm to do exactly what we're telling it to do. So let's say that now I want to get rid of my hello.txt file. I don't want that one either. What can I do? Well, I can rm-f hello.txt. What do you think's going to happen here? It's gone. Didn't even ask me the question. And in fact, if I list the contents of my directory again, it's gone. There's no undo here. Hello.txt is gone, and I wasn't even asked if I wanted to delete it. What if I want to get rid of an entire directory? The way you do that is very similar to copy. You need to, if you want to delete a directory, you don't just want to delete the directory, you want to delete everything inside of it. And so you use -r to recursively delete a directory. So let's rm-r pset2. I'm not actually working on pset2, so I can get rid of that directory. I hit enter. Do I want to remove the directory pset2? Yes, I do. And if I list the contents of my directory again, it's gone. All right? One more variation on this theme. So I'll clear the screen again, clear everything at the top, hit ls. Now I want to get rid of my pset3 directory, and I really know I want to get rid of my pset3 directory. I can recursively and forcibly remove my pset3 directory. Now you got to be really careful when you're using rm-rf. As you program more, it'll be something you just do really quickly. And in fact, I do it all the time, but it can lead to some disastrous consequences if you accidentally delete the wrong thing. So I want you to be aware that this is an option available to you, but use it sparingly and use it with caution. I know for a fact I'm not working on my problem set 3 anymore, so I'm going to get rid of all those files. And I know I don't want to be asked every single time if I want to delete a file. So I'm going to rm-rf pset3. Didn't even ask me if I wanted to get rid of it. I hit ls, pset3 is gone. So that's all the variations that you can use to get rid of files with rm. The last command line argument that's probably the command line command that's going to be pretty useful for you is mv, which is short for move. Move is basically equivalent to rename. It moves a file from one location to another, the source to the destination. Let's see where using a move might be handy at the terminal window. So I'm in my pset1 directory, and I've noticed something has gone a little wrong. I was working on my greedy problem, but I accidentally named it Greddy. So when I try and run it through check50, it doesn't really work. I do have a couple of options. We could do what we've done before, which is to make a copy of the file. I could copy Greddy.c to greedy.c, right? Hit enter. I see that both files are there. And then I could rm to remove Greddy.c. That gets rid of it. So that would work after I confirm that I want to get rid of it. And I effectively have renamed Greddy.c to Greedy.c. I copied it and then removed the original. But that's kind of a multi-step process, and certainly there's a better way. In fact, there is. So let's hit Control L just to bring this back up and list the contents of my directory again. So let's say, oh, I made a mistake. Actually, we did want to call that file Greddy.c. In one fell swoop, I can type move Greedy.c to Greddy.c, hit enter, and now I didn't have to copy and remove it. I just was able to rename it, one-stop shopping. Now, there are a lot of other basic command line utilities that you can use with the Linux command line, and we'll be discussing a lot of them in the future in CS50. But for now, I just was able to rename it, one-stop shopping. Now, there are a lot of other basic command line utilities that you can use with the Linux command line, and we'll be discussing, I made a mistake. Actually, we did want to call that file Greddy.c. In one fell swoop, I can type move Greedy.c to Greddy.c. Hit enter, and now I didn't have to copy and remove it. I just was able to rename it, one-stop shopping. Now, there are a lot of other basic command line utilities that you can use with the Linux command line, and we'll be discussing a lot of them in the future in CS50. But for now, just getting your feet wet with working with this terminal environment, these 5 commands should get you pretty far in navigating around and working with files in your IDE or in whatever Linux-based operating system you're using. If you're curious and you want to look ahead a little bit at some of the command line commands we'll be using in the future, here's a list of a couple of the more common ones. I'm Doug Lloyd. This is CS50.